Before we start, you can see there are two QR codes. One is our recently published Data-centric AI survey. And after its release, like a couple months ago, it has received a lot of attention. And the second one is a GitHub repo, which lists a lot of like resources, papers, competitions, and this and that. So just in case if you wanna get access to more materials, this will be the hub. Okay, welcome to the tutorial. My name is Ben Hu. Today we are going to talk about data-centric AI, including fundamental concepts, techniques, and some algorithms and future perspectives. And this talk will be delivered by Dao Chen, Henry, Fan, Siri, Na, Huiji, and I myself. So we're from Rice, Airbnb, Wake Forest, and Texas A&M University, respectively. Okay. Mainly, so we have been working on models for decades. Okay, that has been a focus. However, I mean, after just so many years of traditional statistical learning methods, machine learning methods, deep learning methods, and surely recently large language models, large models, just so many models. And the community has been well overwhelmed sometimes to select the right models to work in a particular application. And starting from the very beginning of data science journey, it has been a lot of discussion how we are going to prepare the data, how to evaluate an application, and how to deploy the application, how to deploy the model in the specific application. And there has been a lot of discussion. But starting from very recent years, it has been somehow emerged as a concept called data-centric AI. And although some people have dedicated a lot of efforts in investigating this, such as my group, but still, I would say this community, this topic, it is still in the very early stage. So the main purpose of this tutorial is to give you a high-level idea of what is data-centric AI and how we're going to really deal with this problem as a whole. Because previously we do have a lot of dots already investigated about how to connect everything together as a big picture. So this is the main purpose of the tutorial, to introduce everything from training data perspective, inference data mainly, how we're going to evaluate, and the data maintenance, and what are the available benchmarks. And in addition to that, we do have ethical and unfairness issues we observe in many applications. And at the end, we will see some like real-world industrial applications to showcase why data-centric AI is so important, why I will call it DCAI, okay? Why DCAI is so important, and how DCAI is like really executed in industry. I will be taking care of the first part of the talk to give you hopefully a high-level idea what is data-centric AI. So I would like to quote the definition offered by Andrew Ng. Data-centric DCAI is a discipline of systematically engineering the data used to build an AI system. Okay, this is a very brief and high-level introduction, but throughout the whole talk, we're going to try to connect why DCAI is so important and how DCAI will be developed, evaluated, deployed, largely using recently developed large language models as an example, as well as industrial applications throughout the whole talk. And here I would like to emphasize and distinguish the traditionally we have been discussing a lot of data-driven efforts, okay? This is fundamentally different from what we are going to talk about today about data-centric. So data-driven really emphasize the use of data to guide the AI development and deployment, which typically still centers on developing effective models. That's why I would say, if not identical, it will be similar to model-centric AI. So previously we have a whole data, okay, already prepared, and we assume the data is clean. That's why what we want to do is like traditionally, okay, we will divide the data we have at hand into training data, testing data, and we want to develop a model we want to select and develop a model based on the training data, right? And the trained model will be evaluated on the testing data to see how it performs. And if it doesn't work well, we will go back to select another model to try or tune our hyperparameters to make this model work. But now it's like we want to somehow, because like there are just so many models, we have like tons of models to select. We have hyperparameter tuning methods already developed. But now we want to say, okay, how about we go back to see how the data is prepared, is collected, and how we're going to really make use of the data in our to boost the performance of our applications. And as I remember many years ago, I mean, in data science journey, we have heard this concept called garbage in, garbage out. So it means like if the data quality is low, no matter how good the model is, we cannot get like good performance in our application, right? So this is the main purpose why we need to engage data-centric AI. At the same time, I would like to showcase several AI breakthroughs or milestones in the AI journey to see the need of data-centric AI. So here we list a few, including the speech recognition, IBM Deep Blue, and AlexNet, AlphaFold, and recently large language models, GPT 3.5, GPT 4. As we can see on the last column of this table, almost for all of these like important milestones or AI breakthroughs, they are corresponding to the development of a corresponding, I would say, not only high volume, but also high quality data, right? So as we can see for IBM Deep Blue, so 700,000 grandmaster chess games were like included in the training data. And very recently, there was a debate whether large language model, whether ChatGPT has a lot of scientific value. There was a debate on Twitter. So whether or not this is a scientific breakthrough. However, no matter what, it is definitely an engineering breakthrough, right? Because everybody has been benefited from this kind of breakthrough. We have experienced the very good performance, top performance offered by ChatGPT. One of the reasons behind this is like how we are going to really collect, manage, and integrate high quality human feedback in the loop of this reinforcement learning, right? So that's why we can see how important the data is in many of these like AI major milestones. And here data is of course is a driving force when model design becomes more mature. Starting from 2017, the transformer paper was published. But back then, I mean, except the hardcore like NLP community, it doesn't really attract a lot of attention until very recently, right? Until recently, ChatGPT attracted a lot of like attention from the community, from the general public, from every single domain. Okay, and the main reason, I mean, the technology infrastructure behind the training of GPT-1 to GPT-4, surely there are some like development, but comparing to the growth of the data, this is just so important. Especially this wave of human feedback with in reinforcement learning. This is just so important to power our GPT 3.5 and GPT 4, which is fundamental techniques used in ChatGPT. And not only the data size is increasing a lot, but also the data quality has been emphasized a lot in the science and engineering efforts. And so it is very interesting. When the model becomes very powerful, sometimes like not only the training data is so important, but also sometimes we only need like engineering the inference data. So we don't need to worry about the model when it is like good enough, such as those like foundation models. And this is probably the ideal, probably the next step. We want to say, oh, we have a universally working model and we don't have to worry about the model. And this is this gives people hope. We have somehow to have one tool to feed all of the applications, such that we will be able to like just only need to engineer our inference data, such as prompts in chatbots. And here we show several examples. We don't need to touch the model at all. It is fixed, basically. And this is the major development happening in many applications. as well. And also, I would like to highlight another application, segment anything, published early this year. And it is largely attributed to an annotated data set with over 1 billion masks. And this is like 400 times larger than the existing state of the art, the previous state of the art. Segment anything has 3 stages, mainly of labeling. Okay, assisted manual stage, semi-automatic stage, and fully automatic stage. And as we can see, those numbers, they're just scarily large. Okay, the data has been very carefully collected, labeled, deployed, and making use of. And also, surely because of its like power, it attracts a lot of attention from academia and the industry. We can see the exponentially grows number of papers published in we can search by Google Scholar with the phrase data-centric AI. And also we have been seeing a lot of like competitions happening in the community. We have seen like offered courses, which is a great source for us to like dig into even more details. And also we have seen some like events, and also this is a very hot topic in industry and powering several like very popular startup companies, including Landing AI, Snorkel, Scale, how to help people, how to help startups, middle-level companies to label their data, to better prepare their data towards better performance in their downstream applications. They are just so popular. Okay, so I believe I have emphasized a lot about the importance of design. So here, but still, we are computational people. We would like to come back to the real world, how we're gonna really be useful, right, in our own applications. To do this, here the whole framework will be organized in this way. We will try to provide like concepts, algorithms in these aspects in terms of training data deployment, including data collection, labeling, preparation, and so on. And traditionally, we have reduction and augmentation. Recently, augmentation has been so popular. And also, we would like to say, we have like built up a model, but we would like to somehow see how it performs through engineering our data by eliminating those possible noise, by eliminating those outliers and so on, this and that. That's why we have to have effective inference data development, including in distribution, out of distribution evaluation, as well as prompt engineering. And at the end, we would like to discuss how we're gonna ensure we have a very effective like data maintenance, including data understanding, quality assurance, and storage and retrieval. And specifically, through this tutorial, we would like to answer these following 3 research questions. The first one is, how can we construct the right training data to improve the performance, including, again, how we're gonna collect the data, how we can label the data, prepare the data, and perform the data reduction. Most of us, if not all, we have been familiar with like a feature selection, feature reduction, right? We do not want to make use of the whole feature set. But now it comes to the age of how we're gonna really identify the right like samples, because some samples they may lead. So making use of all of the data samples, sometimes they may introduce noise. Sometimes they will make the model inefficient, model training inefficient. And how we're gonna deal with that to make sure we can have a somehow optimum subset of the data instances. And then sometimes to bridge the semantic gap, we want to make sure the data will be augmented towards some like purposes. The second question we would like to answer through the tutorial is like, how can we construct the right inference data to evaluate the model or probe knowledge from the model? So I can give you a very simple example. So in some of our collaboration with hospitals, there is a phenomenon called a shortcut. And so we were giving a tabular data. Each row represents a patient. Each column represents one of the features in EHR data. And we have built a, near to perfect model, okay, very high performance to predict whether or not this patient will develop, has pneumonia. Okay, however, when we send back this model to our physician to say, hey, we have achieved just a tremendous success. It's just with so high performance, but it was kicked back because unfortunately, one of the feature, it is improper, which is a hospital ID. It appears in our top listed features. It turns out that this is one of the most contributing factor. However, through the evaluation manually by the physician, the hospital ID at the time of the patient being admitted, it is not really informative. The reason why it is informative because the data is badly prepared. Because the hospital ID mainly indicate whether this is a pneumonia-related hospital, and inherently introduce some bias into this preparation, and that's why how we're gonna really deal with this kind of out of distribution evaluation, and how we're gonna involve human efforts into the process of evaluation. So this is just so important. The third question we would like to answer is how can we ensure the data is right in a dynamic production environment? Because data just evolves so fast, and the application is evolving very fast, and the data distribution is shifting a lot. So how we're gonna deal with this using effective tools? And what are the available tools? So before we dig into the details, I would like to also introduce several DCAI trends. The first one is called automation and collaboration. Because to keep pace with ever-growing size of available data, as we can see, especially this wave of foundation models, we just have experienced so much growth of training data, and how we're gonna deal with that. And we need more efficient algorithms to automate this process and incorporate the human knowledge through automation and collaboration. Automation includes for example, programming automation, learning-based, pipeline-based automation, and collaboration involves different ways of modeling and incorporating human knowledge. The next trend I would like to introduce is we would like to talk about data today. However, data model boundary is just so blurred, especially because of foundation models. It's just continuously being even more blurred. Here, I would like to give you one example. So originally, we want to prepare synthetic data set for hospitals, and this is also another important application in finance industry, because JP Morgan is pushing so hard to generate synthetic data to facilitate the collaboration and engagement with external parties. For hospitals, for financial industry, their data, I believe many other applications, the data is just so sensitive to share. That's why one effective way to bridge the gap is to generate effective, high-quality synthetic data. And this is one way of doing so. Not directly through the data, but also using models as a container of data so that we are able to generate high-quality synthetic data. And the idea is very simple here, actually. So the first step is we already have a good understanding of our application. For example, if you want to do patient phenotyping, and we want to really provide a very clear and specific task description to ChatGPT, and through multiple rounds of prompt engineering, our hope is we will be able to identify the optimal prompt, such that the prompt will be fed into ChatGPT towards a very effective synthetic data generated by ChatGPT. So in this application, the model itself will be used as a container to provide data for future different purposes. And another example, I would like to show the blurred data model boundaries for example, semantic gap, semantic similarity is one of the probably the most important problems in text mining. Okay, because we want to evaluate the semantic similarity between short terms, phrases, texts, and this has been a long-standing problem in NLP domain and the text mining domain. And here, using large models such as ChatGPT could could like somehow mitigate this problem. Here we show an example. So original criteria is like, oh, how about we like, we want to generate some like, we want to return two statements that are the same as the next statement, and they must be semantically identical using different, but however the terms, the language they use must be different from each other. And then each of these sentences, clinical diagnosis of this stroke involving cerebral cortex can be extended to like two sentences, two statements. They are somehow share identical semantic meaning. However, they use completely different statements. And the same for the second one, serious systematic hemorrhage in the past 30 days. And the two augmented statements are, there are severe case of systematic hemorrhage in the last month. Last month, certainly it's the same thing with the past 30 days. And also the second one is the patient experienced a significant episode of internal bleeding within the past 30 days. Internal bleeding, it is the same as the medical problem we mentioned in the sentence. That's why the two sentences can be served as a data augmentation, and it will be potentially used to bridge the gap of semantic meanings, because different physicians, they tend to use different statements in their clinical notes. Different hospitals, they have different like a procedure in preparing, in using those like clinical notes. And this is an effective way of doing this. And surely from this example, we can see the data model boundary has been blurred. So that's why it's not that clear boundary. Okay, so next step, Daochen will take over from here to start the discussion of those like techniques and algorithms. So before doing that, so you can see we have a perspective paper, short, precise, easy to read, and we have a long survey paper, also the GitHub resource for just providing more comprehensive materials. Okay, thanks very much. Before I hand it over to Daochen, any questions? Okay, cool. So I will leave the stage to Daochen. Yeah, thank you.
Yeah, thank you, Professor Hu, for giving a very high-level introduction of data-centric AI. So data-centric AI is a very large topic. So now we try to dig into it and to introduce the corresponding techniques for the training data, inference data, and data maintenance and fairness and bias. So I will talk about the training data development first. So the outline of this section is, firstly, I will give an overview about training data development, and then I will give techniques. The first is data collection and labeling, so which is something like how we can create a data set. And the second part is data preparation, data reduction, and data augmentation. So it's more like how to refine the data set. So it's given a data set, how to make it better. And the third one is most interesting, is like we will do some case studies about how to apply data-centric AI to the problems we care. The first one is training data development for large language models. And the second one is training data development for graphs, such as graph neural networks and knowledge graph. So firstly, so why we need to develop training data? So it's actually very obvious, right? So firstly, so we to learn a machine learning model, the first step we need to do is to create the right training data. And sometimes we need the label data. So we need to collect the data and label the data, label like the image is a cat, and then this image is a dog, and so on. And additionally, so appropriate data pre-processing techniques are also needed. So which includes data preparation. So data preparation is like given some raw data set, and we try to do some filterings and to remove the data, undesirable data, and or do some refinement, like do some normalization, do some scaling to make the data easier learnable by the model. And secondly, data reduction, which means we try to transform from a large set of data into a small set of data. So which is very important for two reasons. The firstly is sometimes there could be some redundant information. So for example, in many cases, we have imbalanced data. So, and we sometimes we may want to undersample the majority samples, so to balance the data. So those data could have some irrelevant or redundant information. And secondly is, so when we reduce the data size, so it also makes the model training more efficient, and we can have a faster iteration. So this is very important, especially in industrial applications. So because sometimes when we train a model, it could take several days. So if we can reduce the data size and train a model on it and to achieve the similar result, this will be a huge benefit for the engineers because they can save the time in the iteration. And finally, data augmentation, which is also very important because in many cases, we only have very limited number of samples and we want to learn more from limited information. So how we can do this? We can do some augmentation. The most intuitive example is in images, when we can do some flipping and to create create a lot of dogs, although they are all originated from the same image. So firstly, I will talk about data collection. So which is the most important, because the source of data kind of determine what model we can have finally. So I first listed several common strategies, which includes a direct data collection. So which means we just directly collect data from the sources. And the second one, which is very popular, especially in the database community, is called the dataset discovery. So which means we create new dataset by integrating the existing dataset. The main reason is like in the common world, for example, in a company, so we may already have a lot of dataset. So when to do a machine learning application, sometimes we may not even have to collect some new data. We just merge the existing dataset to create a new dataset. And thirdly, data synthesis. So which means we can synthesize some data for our own purpose. And finally, some hybrid methods that we do some integration, do synthesis, and collect some real data and to create our own dataset. So some things to keep in mind. So how to do a data collection. So the first thing is data coverage. So the question is, can the create data set cover different scenarios? So because to train a machine learning model, our goal is actually to make the model general as well to all different scenarios. So of course, to achieve this, we must have a very, very good data coverage. An example is the GPT model. They kind of collect data from different languages and from different sources. So that's why the GPT-3, ChatGPT, GPT-4 can generate as well to different scenarios. And secondly, is the data size. So we need to have a proper data size, neither too large nor too small. So why? Because if data size is too small, so we may end up with a very limited model that cannot generate as well. But if the data size is too large, so which is impractical to train a model, so which is also not good. And thirdly is the noise. So when we collect data, so the data could have some flaws, so such as the label noise, and the data itself could have some noise. So we need to keep this question in mind when we do the data collection. So let me list a few examples. The first one, the dataset discovery. So as the number of available datasets grows, it becomes possible to amass the existing datasets of interest to collect a new dataset. So to give an example, so this is a system created presented in ICD 2018. So they build an enterprise knowledge graph for datasets. So they use source retrieval query language, so which is something very similar to the SQL, and to search for datasets of interest. So this system could be applied in many scenarios where we have some datasets, especially for some large companies where they already have a lot of dataset. So another one is the data synthesis. So in for example, in some cases, it could be more efficient to synthesize data set that contains the desirable patterns than to collect these patterns from the real world. Why? Because sometimes, some patterns could be counterfactual, right? So we may not be able to really observe it in the real world. And even if we can observe it, so it could be very noisy. So to give an example, so in anomaly detection, it is often very hard to collect sufficient real anomalies because, as anomaly suggests, anomalies are really rare. So, and sometimes we have very strong assumptions about anomalies. So So like how the anomalies should look like, and so where should they located? We may not even be able to find those patterns in the real world. So so that's why actually in many papers you can find researchers often insert anomaly patterns into the anomaly-free data set, so to synthesize the anomalies. So to give an example, so in time series, so it's hard to time series data, as you know, is actually very noisy. So such as the EEG data, UCG data. So it's hard to identify a pattern within it. So to do the experiment, so one way to do this is to do data synthesis. So for example, in this work, revisiting time series online detection, definitions and benchmark. So actually the paper has provides several synthesis strategies. So which kind of model the anomalies as a parameterized combination of trend, seasonality, and sharpness. And then, so different kind of point-wise or pattern-wise anomalies can be generated by altering these parameters. So for example, in this figure, so these are generated anomalies based on the anomaly-free data set. So as you can see, so the first one is a point-wise anomaly, which means the one point is different from the other data points. And the last one is the pattern-wise anomalies, which means kind of a segment is different from the other segments. So actually, so this kind of patterns are hard to be identified in real world because real world data sets are kind of have a combination of different anomalies and there are a lot of noise. So when we do the experiment, we don't know which is the noise and which is the true anomaly. So if we train a model on it, that model will be hard to explain. So if we can synthesize the data and train a model on it, so we can ensure that the model has the desirable behavior. That's why we need to, data synthesis plays a role in data collection. So then we go to the data labeling. So in addition to data collection, so in many scenarios, we often rely on supervised learning, which means we need to have the labels. So there are actually a lot of strategies to label the data. So we all know that labeling data is very important because if there is some error in the data, the model, of course, will kind of overfeed to the errors and lead to a false result. So there are some common strategies, so which are some traditional strategies. The first one is crowdsourcing. The high-level idea is to break down a labeling task into some small and more manageable parts so that they can be outsourced and distributed to a large number of non-expert annotators. So this is commonly happening on the cloud. So for example, in the Amazon, so AWS, so they have this kind of crowdsourcing services. So they just assign this labeling task to some non-expert, and then they do something like a majority voting and to ensure the data quality. So the pros of this is like crowdsourcing can make the labeling process more manageable. The cons is like because they are non-expert, we cannot ensure that data quality is high enough. And another strategy is semi-supervised labeling. So it's actually very similar to semi-supervised learning, which means leverage a small amount of label data to infer the labels of the unlabeled data. And active learning, which means which is an iterative procedure that involves humans in the loop. So in the iteration, the first step, we label a data points, and then make use of this label data, we train a model and use this, based on this model, we label another data points. So which is a human in the loop procedure. And the final one is distance supervision, so which is also very hot since decades ago. So the idea is to assigning labels by leveraging external sources. So as an example, so in the we can use a large language model to do some labeling, right? So given some text data, we just use some prompts like, so could you tell me the sentiment of this sentence? And then the large language model can say, okay, it's a neutral, it's positive or negative. So this is an example of distance supervision. And final one, now I will talk about some emerging strategies, so which only appear in the recent several years. So which is kind of an advancement of the traditional method to make the labeling process more efficient. And some of these strategies are even being used in some AI data companies, some startups to commercialize. So the first one, which is very famous one, is called data programming. So which means inferring labels based on human design labeling functions, which I will talk in detail later. The second one is RL-based active learning. So which is very popular, especially in large language models with reinforcement from human feedback. Let me first talk about the data labeling. So the idea of data labeling can be summarized in this figure. So the main assumption of data programming is like instead of some labeled instances, we have some labeling functions. So for example, if we want to label the news sentiment, a news category. So for example, if the title of a specific news has the word of basketball, then it will be very likely to belong to the sport category. And if it is talking about soccer, football, of course, they're also sport category. So the idea of labeling function is like we humans design some rules about how to classify the documents. So for example, if this document contains the word of basketball, then this document belongs to the category of sport. So we create a lot of rules like this, maybe hundreds of rules. Then the goal of data labeling is, given these labeling functions, so how can we infer the labels of all the data instances? So which is actually very challenging because for humans, usually this kind of labeling functions are very accurate. However, they can have a very low coverage because there are many cases that we cannot think of. And the other issue is sometimes there could be some conflict. So for example, if one news has the basketball and at the same time it has the word of bank, then so whether it should belong to the sports or belong to the financial, right? So how to resolve this conflict? So there are a series of research, I think more than 50 papers working on this direction. So they try to use some graphical modeling method, statistical method to resolve this conflict and infer labels for some unknown cases. So here is a benchmark, so which can give a summary of the existing method. And the second one which is very popular recently, is called reinforcement from human feedback. So which is actually the key technique behind ChatGPT and GPT-4 to do the alignment. So the high-level idea is actually can be summarized in 3 steps. The first step is collect demonstration data and train a supervised policy, so which has nothing to do with reinforcement. And the second one is very important. So that collect the comparison data. So how it works? So it's like so in the traditional human in the loop. So we usually just label the data. So it's like in each iteration we may label this data belongs to category A. This data belongs to category B. So however, in reinforcement from human feedback, they do a comparison. So which means they ask the human, given A and B, so is A better than B or B better than A? So in the actual implementation, actually the humans will prompt provided with, for example, maybe 10 outputs given an input. And the humans will rank these 10 output and to see which is the best, which is the second best, and which is the worst. So, and then given this ranking, so we actually have pairwise comparison of which one is better. And then we use reinforcement from human feedback to learn a reward model. And then we use a reward model to tune the policy network. So in this process, actually we use reinforcement to collect the human feedback. So why? Because the reinforcement process is actually aligns well with humans. So it's like for reinforcement in each step, so we need to take an action given a state. So in the labeling process, actually in each step, the humans will observe some sentences and the human will give a feedback. So combine this together, so which is a perfect match. So that's why reinforcement from human feedback can work really well to incorporate human knowledge. So another work, which is actually the work from myself, which is called Meta-AAD, so which also leverage reinforcement to do the labeling. So this work is actually done on the anomaly detection domain. So the idea is to learn to select the most important data sample for curing humans with reinforcement. So it's actually one challenge in active learning is, so the whole active learning process, like in each iteration. So for example, given 1,000 unlabeled instance. So in iteration 1, we need to select one unlabeled instance out of the 1,000 unlabeled instance and present it to the human annotator the human will label it. And given this new label, and we will decide, okay, which unlabeled instance will be selected again to present humans. So this decision space is actually very large. So you can see in the first step, the decision space is 1,000 if there are 1,000 unlabeled samples. And in the second step is 999, and third step is 998. So this, if we multiply them together, decision space is really huge. So how we can make the optimal decision? So in this paper, so what we do is we align this with a reinforcement procedure, because they're naturally aligned. So in reinforcement, in each state, we need to take an action, and given the action, we transit to the next state. And in the next state, we take another action and transit to the next state. And finally, we have a reward signal to indicate how well this decision is. So in this work, we kind of implement this idea in active anomaly detection. So we use the actual performance as a reward feedback to update the reinforcement policy. So after data labeling, so I will just briefly summarize some recent ideas in data preprocessing. So data preprocessing is not new. There are a lot of strategies like the scaling data, normalizing the data, and many others. I will just talk about some recent papers. So the first one is the automated data augmentation. So it's like currently, there are a lot of augmentation techniques, but we don't know which one use. Automated data augmentation aims to use some search algorithms to automatically decide which one is good. So as Professor Hu has mentioned, so one trend in data DCAI is actually, so the algorithms become more and more automated. So we don't, in some cases, such as data preprocessing, we don't want the humans to involve too much. We want the algorithms to decide by itself which is better. And the second is automated data balancing, so which is actually data reduction. So it's the oversampling. So the use cases like in imbalanced cases, so we have some majority instances and some minority instances where the number of majority instances is much larger than the number of minority instances. If we just simply train a classifier on it, so what would happen is the performance will be dominated by the majority instances. So this is because how the loss is designed, how the algorithm is designed. So one strategy to balance data is to do the oversampling. So it's like how we can do some duplication or do some combinations based on the minority samples to balance the data. So this is also very challenging decision problem because there are so many ways to do this oversampling. We can do random oversampling. We can combine two data points and select some data point in between and many others. So in this work, so an RL agent is used to select how to do this sampling, so which also follows the trend of automation. And third one is automated data cleaning. There's a recent work called Alpha Clean. So they use some search algorithms to design the best data cleaning strategies. And finally, we automated pipeline search. So actually, in the machine learning is often a pipeline. So in the first step, maybe we need to do the data preprocessing, we need to do the data scaling, and finally train a model, which is a long process. So to optimize the performance, so we usually need to find the best data pipeline and the model pipeline within the whole search space. So in this work, so a data pipeline search algorithm is developed for anomaly detection. So now I will just go through some case studies. So about how to apply the trained data development strategies to different scenarios, such as the large language model. So actually data quality impact the performance of large language models a lot. So regardless in the pre-training or fine-tuning phase. So for example, in a recent survey of large language model, they have summarized so the typical steps of getting the high quality text data for large language model, which from the raw data corpus, we have some quality filtering, deduplication, which means we remove some duplicate text, and privacy reduction and tokenization. And there are many steps about how to obtain the high quality data. So actually in the realm of large language model, so the main driving force is actually from my opinion, is the high quality data. So because the model can only behave what the data look like. So another case study is, so in different applications, the data also plays an important role. So for example, in the finance domain, so if we want to create a large language model for domain-specific cases such as finance, so one thing we need to do is to create the right data set. So for example, in this work, a lot of data sources, data curation pipeline have been developed to train and fine-tune to obtain a financial large language model. And similar things have also been done in biomedical. So in this paper, Biomed GPT, so to train a biomedical GPT, so the main bottleneck is still on the training data. So how to get the training data, right? So in this paper, they create a data curation pipeline from different sources, including the vision and language. And you can see there are a lot of images and many others. So all of them, as you can see, the data quality and quantity play a very important role in the training and development of large language models. So in addition to the pre-training and fine-tuning, so there's alignment also plays a very important role in large language models. So which is actually, I have talked about the reinforcement from human feedback. So why we need to do the alignment? So because when we do the pre-training, so we only train the model to behave so based on the text. However, sometimes the model may not behave as what we expect, as humans expect. So in these cases, we may need humans to provide some feedback about which is better and which is worse. So which is actually still centered around the data. So actually the humans provide feedback on the data to train the model. So a common strategy, of course, is the reinforcement from human feedback. In addition to this, there are some supervised fine-tuning strategies and some others. So a second case study I want to share is train the data development for GNNs, for graphs. So because GNNs or knowledge graph are become increasingly popular these days, and how can we apply these ideas in GNN? So the high-level idea is actually very simple. So in the model-centric development, which is the majority of our current study, is the graph data is fixed, given some standard data sets like Cora, Scicere, and many others. And then we just iterate on the GNN models to get the prediction. This is our current workflow of GNN research. So, but is it the right thing to do? So it's hard to say. So how can we know that whether the data do not have flaws? Maybe the data itself has some labeling errors. Then data could not have a very good features, right? So the data-centric approach to do this research is we iterate on both the graph data and the GNN, and in order to improve the prediction performance. So I will just list a few examples of recent efforts in this direction. The first direction is called graph structure learning. So the idea is to optimize both the graph structure and the corresponding GNN representations. So the motivation is in a graph, and sometimes the connection between two nodes could be wrong for different reasons. And there could be some missing links in the graph. So if we can correct these errors, we may be able to get a better performance. So this kind of research can be generally divided into three different strategies. The first one is pre-training. So which means we first do the structure learning, and then given the learned structure, we train a GNN model. A second strategy is called iter training or iterative training. So which means in each iteration, we alternatively update the structure of the graph and update the GNN weights. And third one is co-training. So we just update them together. So there is actually a series of work in this direction to learn a better graph structure. So in a recent benchmark paper, OpenGSL, a comprehensive benchmark for graph structure learning. So this figure is actually well listed existing method for GNN training. So this paper actually benchmarks different scenarios based on the according to the accuracy, the space limit, and time limit. And if you are interested, and you can go to this library, and or you can just search OpenGSL. So the key findings in this paper is the homophilous assumption, so which means increase the homophily of the structure does not necessarily translate to improved performance, and the learned structures exhibit strong generalizability, and the most GSL methods are time and memory efficient, which means there are still a lot of opportunities in this direction. So another direction is subgraph selection, and sometimes we may not want to learn from the whole graph, and we subgraph. So to learn a subgraph could be better. So which means in the reasoning, sometimes we may need a 1-hop reasoning, sometimes we may need a 2-hop, and sometimes we need a 3-hop. However, the current GN actually just use a fixed 2-layer or 3-layer graph neural networks, which may not be able to model the GN well. So so in this work, actually, a selector is learned to select the subgraph to achieve the better performance. So another direction is graph augmentation, which means we generate some synthetic graphs to create more training data for improving the generalization of GNN models. An example is the G-mixup. So which kind of do this augmentation is a graphing stage, a graphing mix-up, so which can achieve a better performance. And in addition to do this mix-up before the training, the design of synthetic data generalization could be integrated with the training algorithms. An example is a recent paper, Engage, so which uses the explanation to guide this data augmentation process, which means we use explanation to identify the important features. And then we keep those important features during the data augmentation and do some perturbation in the unimportant features. Another one is the graph condensation. So because the graph is very large, so it will be very expensive, especially, for example, in the inference stage, we need to do aggregation, so which is very expensive. So if we can learn a smaller graph and achieve similar result while learning on this graph, then this would significantly increase the efficiency. So one direction is called a graph condensation. So we should learn a small synthetic graph from a large original data set to train the GNN models. There are different strategies. For example, in this paper, they use gradient matching to ensure the gradient learned on this larger graph and a smaller graph are very similar. So in knowledge graph, so these are similar cases. So knowledge graph could also have flaws. So because knowledge graphs are often automated generated with some tools. So it's possible that there's some knowledge wrong. For example, here, maybe in knowledge graph, it will say the Bill Gates is the CEO of Google, which could be wrong. So can we correct it? So as an example, there's one framework paper called Active Ensemble Learning for Knowledge Graph Error Detection, so which aims to identify the errors on the graph. And this paper proposed a ensemble strategy to ensemble different active learning strategies to improve the performance by reducing the flaws, the number of wrongly connected nodes in the knowledge graph. So that's everything about training data development. So do you have any questions? Yeah.
You talked about performance and accuracy of the graph of the GNN. How do you measure that? It's depending on the application.
Sorry, could you repeat again?
You talked about performance and accuracy of the GNN models.
Yeah.
How do you measure the accuracy of the performance?
Yeah, it's a very good question.
The application, I can give an example.
Yeah, so the ideal case is like we have a perfect evaluation data, so which can tell the performance. But in the research, we may not be able to achieve this because sometimes even the evaluation data could have some flaws. So what we can do in the research is actually we just separate the training data, validation data, and the test data. And then we iterate on the training data to train a model and test it on validation and testing.
Result. Well, who determines what is a valid result? What is a valid graph?
Yeah. I think it's like a chicken egg problem, right? So in order to test the performance, we need to have a correct data set to test the performance, but sometimes it's even very hard to get the correct evaluation data. So I think what I can think of in the scenario is, so we may need to manually examine the evaluation data, maybe a very small set of evaluation data, to ensure everything is correct here, and then use this as the thing for testing. So yeah, I think that's what we could do from the research community. So I'm not sure whether this answers your question.
I wanted an example of an application.
Example of application of graph.
Application, yeah. Well, biology or knowledge graph or something.
Yeah, so one example is so for example in the error detection, so as shown here, so in the knowledge graph there could be some errors in the knowledge graph, right? So because some of the knowledge graph are automated generated, so by some tools there could be some errors, but at the same time, so we could also have some knowledge graph carefully constructed by humans, and we can ensure this graph is correct. So what we can do is we iterate on the data set that is automated generated, and then train a model on it and evaluate on that known good evaluation data. So I'm not sure whether it's a good example. Yeah, thank you. So any other questions? So if not, and I will hand over to Fan, which will talk about the inference data development.
Thanks, Dr. and as well as Dr. Hu for the efforts. So I'll take over from here for the inference data development under the DCAI, the data-centric artificial intelligence. So overall, I want to talk this 4 different sections. And first, I would like to give an overview, basically the differences of the data-centric and model-centric and what we want different from these 2 different paradigms. And overall, I want to formulate this section from the functional roles, which is a little bit different from our survey paper, because I think that may be easier to give you an impression on how we really formulate the things in data-centric AI. So the first functional role I want to talk about is called a granular evaluator. So basically, we want to develop the data and trying to doing a more in-depth evaluation, which is totally different from the model-centric. And also, we want to use the inference data serve as the decision interpreter, which is also giving them more insights, which is beyond a model-centric inference data. And the 4th thing is much more motivated by current large language models, and we also see a lot of potentials to using the inference data as the prompt tuner, such as the prompts, which is currently very hot in tuning the large language models. So let's take a deeper look at, and due to the space limitation, I may just neglect some of the technical papers which we involved in the survey. So if you want a more in-depth information, so please feel free to check our paper. So this is the figure. I think it's mostly common to every audience is here, as long as you have some hands-on experiences for machine learning. So when we fixing the data, this is actually the way how we divide the data. So we hold some data for training, and we have some hard data, which for validation to tuning our model. And then we're having some inference data. We also call it test data to test the performance. So the reason why we're using the inference data here is because usually when we try to evaluate our models and testing the well is pretty expensive. So one of the most straightforward and simple way is to have some data, which having the kind of very similar data distribution as your training one, and so as to evaluate the generalizability of your original model. And also when we're having some of pattern data for inferences, they can also guarantee us a very fast iterations to develop our model. And also using this kind of inference data, it can give us an indicator to see whether our model are converged to the point that we want. So usually these are the 3 kind of the major steps that in model-centric paradigm, why we want to inference data like that. However, in the data-centric AI, we definitely want more. So one of the limitations from this head of data is those head of data is only can give you very comprehensive, this high level indicator of your model performance. And if we want to look at deeper into the data and what kind of the data which are underperformed, usually this kind of the evaluation strategy from the model-centric gonna fails. And also for the head of data, we can only know whether your model get a better validation error or get a better test error, but we can never know what kind of the mistakes happens here. So basically, we want to know more insights through the data, and that is the head of data cannot provide. And the third part is that the head of data cannot tune for tasks. And those head of data are just a static one. And as the humans, we cannot manage to do it to tuning for the downstream task. And this is the third limitation, which we definitely need in data-centric AI. So for the first one, how can we actually have a better evaluation? So this is example for the face recognition. And this is the typical deep neural networks. So when we're having such kind of the AI systems, so a kind of big question we can raise is, how about this model performs on the, for example, for the Hispanic people faces, and whether it's well performed for the Asian faces. So those kind of questions definitely using the head of data cannot be easily evaluated. And that's why we want a more granular evaluation for in the data-centric AI. And also for the model performance and whether the prediction is robust or it is not robust, it's very subtle. So we need some answers in evaluating this data-centric models. And second needs is the interpretation needs. And this is an example when we having a bunch of training data and we train a model, and usually the conventional machine learning model pipeline can only give you a number to see how likely, say this image is a husky or not. But most likely, we only have the limited insights from this pipeline. And more times, what we want to know is what kind of the reasons lying behind this decision, so as to know whether this model are doing the reasonable, ethical, or reliable prediction. So how should we understand the model decision boundaries within the data-centric AI, and how can we really detect whether the model is behaving ethical or fair? And also, how can we acquire the model feedbacks when we're doing the calibration and refinement? So the third thing is the task tuning. So this is example within the large language models, and we can see, assuming that we have a omnipotent large language models, and we want the model specific like tuning for a review classification. And we give the prompt to see what kind of the task we want a model to handle. And we give the task description with the movie review, and we give them some examples, and then we want them to give the conclusions. And so this kind of the example, we can see definitely the inference data in data-centric AI can be something to be interactive to humans. And we do not want to be the static models, only give you a numerical feedback. We want them to be the tuners, exact tuners for the tasks. So let's go to the first part about the granular evaluator for data-centric AI. And the two major technical categories I want to cover. The first thing is called the data slicing, which is very straightforward when you're doing the evaluation. And second is called the noise injection. For data slicing, for example, if just back to the example of the face recognition, if we want to know the model behavior for certain groups, and the most straightforward way is how can we really slice in the data based on the race categories to see what kind of the faces types they are most good at or not good at. And usually this kind of slicing techniques is definitely within the in-distribution data. And for noise injection, we want to evaluate the model behaviors typically related to the auto distribution data, such as the model robustness, to see whether they are robust enough to doing the detection and the prediction. So let's stick into the data slicing part. So this is the one of the representative I want to mention here from Google, and I think this paper is from ICD 2019. So currently, a lot of people using these tools when they doing the in-depth the data-centric evaluation. That is, this kind of the tools they can do the automated slice finding to say which kind of the column combination are the data slices which are underperformed by your model. So this is super important, especially under the current ethical concerns to see whether the people from different races, genders are treated equally. So overall, this methodology is pretty straightforward. So in the paper, they provide 3 different ways in generating those underperformed slices. So the most effective one is the one I listed here, is using a searching one. So yeah. So they use the reference search to searching those different combinations of the features. And we can see usually when your feature space is pretty large. So this kind of models can, this kind of methods can be very expensive in searching. But usually, as long as you have a reasonable threshold for your assumptions, so they can assume having the top K large problem slices in a reasonable time. So from my hands-on experiences, usually I would say the performance is pretty good with the slice finder. So they can give you a much more deeper and granular insights for your data, which you're working on. And the second work I want to highlight is called George from Stanford. And this work is trying to dive deeper into the data-centric problem, which is the subgroup labels. So sometimes we know that our models may be not good at something, but we don't have the explicit labels in our data. So for example, I gave a picture of the water bird, but sometimes in your training data, some of your water birds are on land and some of the water bird on the water. So those 2 labels are not explicitly shown in your data, but your models may be only good at to detect the water bird on land, and they may be very bad at detecting the water bird on water. So this kind of phenomenon in machine learning is called the hidden stratification. So this is also one of the things that the data-centric AI trying to avoid. So how can we handle such kind of the hidden stratification is George, these tools, they present to using the latent representation to doing the clustering. So they found like, even though those kind of the labels are not exactly shown in your data sets, but in the latent space, they can be clustered into 2 different groups very well. So this is the case example from the, I think it's the skin cancer, those kind of medical images. So with patch and without patch, you can see in the latent space, they can be classified very well. So based on this observation, this work present kind of methods to help you to finding those the performance gaps in your data without the subgroup labels by estimating the subgroup labels with the generative models. And I give a very brief illustration, graph illustration on the top corner. For Z is the attributes, and V is the image features, and X is the instance, and Y is the label. So you can see the attributes controls the generation of the features as well as the labels. And the all through some of the mapping function G to the final instances. So this generalizing on the latent generation process of the whole images, and the sufficiently considers the attributes, the features, and the instances into the whole process. And in my opinion, I think this is the very decent illustration about a data-centric evaluation. And I think this is what the data-centric AI evaluation should be. So talking about noise injection, so we can also utilizing the noises to evaluate the different aspects of the model. So one of the very well-cited paper in SAR 2018 illustrating that when you're trying to injecting the noises of your data, so you can find your models can deteriorate the performance very quickly. So this is the example for the model translation. The model is called the character to character. And when you try to injecting the different type of noises into the model, you can see the translation score is dropped significantly. And the 3 different types of noises investigated here is called the keyboard, which is usually some typo, and the natural one is some human errors, and the random noises is usually some of the perturbation which are simulated. So as we can see, by the way, so the y-axis is the variance of the model weights. So usually when you're having some of the random noises together trained with your model, and it can significantly enhance the model's ability in doing a prediction. So for the adversarial noises, and this is one particular type of noises for injection, which can help evaluating in the data-centric paradigm. And for the noise contraction, and we can utilizing the fast gradient sign method to generating some noises which can easily fool the models you have. And those kind of the adversarial samples usually can be see one of your drawbacks of models. And in the data-centric AI perspective, it can be also very useful to evaluate whether your model has the secure or reliable prediction. And using those kind of fast gradient sign, just one typical method, and also we can utilizing some of the adversarial rules to generating those adversarial sample with the noises for inference as well. So for example, in the Rogro, one of the paper from the natural language processing is to finding some of the adversarial rules by changing some of the colors with the equivalent semantic meanings, but the prediction results going to change significantly. So those are all the possible ways of deconstructing those adversarial samples for inference, and those inference data could be also very useful in evaluating robustness of the model. Another type of the noises I want to mention is called calibrated noises. And usually this kind of noises is intentionally injected into the model, and they can be very useful to evaluating the data privacy as well as the model security. So this direction usually is highly related to the one of the community called the differential privacy. So a lot of people trying to utilizing these differential private noises to try to make their model more secure and private, so that the attackers they can be very challenging to really extract the exact things and information inside the model and data, and which could also be one of the effective way for us to evaluate our model whether they are maintained or developed in a secure way. So beyond this kind of the noise injection and as well as the data slicing, so actually with the rising of the large language models, more and more perspectives are rising, and definitely people beyond the adversarial robustness, the OD robustness and the privacy stuff, and those GPT models, they're trying to give you more rising perspectives for evaluation, which is trying to give in the even more granular evaluation. And we can see for specifically for GPT models, they're also trying to formulate ways to evaluate the toxicity, stereotypes, and also the machine ethics. So as we can see, so as the era is going to proceed, so more and more aspects is rising. And I believe these granular review, granular evaluator going to become more and more complicated. So yeah, this is just some current quick summary about this area. So for a decision interpreter, I believe this is the second functional roles we want to mention here for under the data-centric AI. So first, the technical categories I want to cover is the cloud algorithm recourse. And this is from the instance level to see for each instance of the data. So how can we really interpret the model behavior? And from the group level, I also want to slightly mention the distribution shift. And I believe this part should be covered more by Siri later. So for the algorithm recourse, it can be overall formulation can be shown in this figure. So overall, when we consider a binary classification, so those kind of the recourse samples for the inference purposes, they can be constructed to be some samples which are slightly go across the decision boundaries. So those samples can be very useful because it not only tells you why your model fails at some point, it actually can tell you how you're changing your model from one decision to another. So this mathematical formulation is pretty simple. Basically, it tells us how to finding those recourse samples for evaluation purposes. So we're trying to find some samples which called X star, and those samples should be having the minimized distance from the query sample queue and themselves. So your original prediction should be the -1, which is the net things we do not prefer. And the positive one means the labels that we prefer. So when we're finding those kind of the samples together, we're gonna find how can we really changing from our query samples to the preferred samples. And usually this kind of formulation is under the Granger causality assumption. So in the explainable AI community, people also calling those samples called counterfactual samples. But I also believe should be a very important perspectives in the data-centric AI to developing the inference data to evaluate your model explainability. So the recourse for interpretation, usually having these two major stuff. The first thing is called the rational effect. So as this figure illustrated from the DICE paper from the Microsoft.
喂，干嘛？你打电话打不电话做干很高哩，手机头。
I'm sorry, I think someone on the remote is having
什么电费啊？
Okay, let's.
你乘电费，你乘，再乘。
Sorry, it's a little distracting.
吃饭呢？你也恰饭，司机头。我已经回去学校了， 已经回了。
For the report samples, the first thing is the rational effect. So rational effect is kind of the artistic terms. Actually, the movie directed by Akira in the 1950s. So the rational effect actually means when we having a certain things and people viewing from different perspectives, we may have a totally different conclusions. So here, the rational effect for recourse is actually we have a lot of different ways to flip our decisions. So when we develop some of the inference data to evaluating in a data-centric perspectives, we may have a lot of different ways to interpret your decisions. So this is actually very, very important to justify your model behaviors, and which I think should be a very important standard to.
你再还有多少题？乘上去，我再教。
For the data-centric inference data development. And also the thing is these kind of the recourse can help you detect whether the model having a fairness or ethical issues. So this is a quick example to see the those kind of the bad correlations within your model. So this is the actually gender classification trying to tell whether the people is young or old. So as we can see, the top hierarchy for the perturbation of the other attributes lies in first on the male. So this actually give you indicator that those kind of the age and the gender, they are strongly correlated. So this is definitely the things we want to avoid, and the recourse can also help in such a way. By grouping those recourse together, researchers are also possible to grab a bunch of the recourse set rules to help you better identify those data structures. So for different recourse rules, we can see when we're having some of the sub indicators together, we will know the different branches of the model behaviors. And this is also very useful when you are developing your models in the inference stage. And for the data shifts, and this is also one of the major important when we viewing our data in a group. So this is example for the data changings varying with the time. So when we're having a dog from the past and now, and usually indicates the different status with your training data and test data. And the world is changing, but the models at hand may not. And usually we use the KL divergence to measure distance with the two different the data distributions so as to having the quantitative measurement for this kind of data distribution. And one of the important work in this area is to monitoring the data shifts within your inference data.
那你要出口独立，天天搞我请司机头。
Utilizing some data dimensional reduction techniques and trying to condense these two different data distribution together, and then trying to see whether
闭嘴！
fitting or not fitting with a certain hypothesis threshold. And the overall takeaway for this message, for this paper is they're gonna using some of the average embedding from these distributions, and they use the MMD as the metric to see whether these two distributions are similar or they are different. So when MMD is large, they basically indicate a very significant distribution, and they should be aware for the developers when they training their models, because this is definitely not the things we want when we're having a well-trained model. So for the third function roles, I want to tell about a task tuner within the data-centric AI. And the two technical branches I want to cover first is the fine-tuning, and the second thing is the problem engineering. So for the fine-tuning, the people currently nowadays are trying to give in the fine-tuning 3 different categories to define the different technical solutions. So first is called a feature-based approach. So for feature-based approach fine-tuning, the basically is when we're having those pre-trained models, the transformers, we're gonna frozen the weights. And the only thing we're gonna train is the new classifier. So you can regard those pre-trained model as the feature extractor. So after we having the proper feature extractor, we're gonna train the proper classifiers for different downstream tasks. And this usually give you a much more easier ways to prepare a model. Now, fine-tuning type 1 is a little bit different from the first feature-based one. Is we want to make it even more aggressive, that we want to fix the classifier architecture. We don't want to change anything in the model architecture for the classifier part. And the only thing is we only utilizing a small bunch of the data to fine-tuning those kind of the final layers to having a better performance. And the fine-tuning 2 is much more aggressive to fine-tuning with the small amount of data to both the pre-train and the classifier head, those kind of the model components. And usually this kind of the tuning strategies involves much more parameters to tune. So usually it's need much more resources as well as time consumption. And this is the common standard for the relations for between the training efficiency and modeling performance. So as we can see, when we want to have a better modeling performance, typically we want to tune in more efficient. We want to tune in more parameters as much as possible so as to having a better performance. But at the same time, we definitely will need to handling much more parameters to doing that. And this gives you a lot of pressure and the challenging when for your machines as well as your platforms doing this development. And this kind of the tuning actually gives a more kind of rising areas. How can we do the parameter efficient tuning? So parameter efficient tuning is just that we want to get the benefits from fine tuning, but at the same time, we don't want to handle too much parameters during this process. So as this figure illustrated, so basically the parameter efficient tuning is trying to appending a small bunch of the parameter models into this fine-tuned LLM, and we only train those the black box, which has appended as the red one. So this significantly reduced the number of parameters for tuning, but at the same time for manual tasks, these things are very decent and a very simple solution to get your own customized models in data-centric AI paradigm. In my opinion, I think 2 most important work in the parameter efficient tuning is the first one is LoRa. And LoRa is actually, I give some technical details here, but LoRa basically is having a much more smaller model appended with the original model body. And they fixed the original operation LM and only tuning the small model tuners appended with the model body. And this is tested to be a very good performance for fine-tuning tasks. And for adapter, this kind of methodology is to adding the adapter on the top of the transformer modules. So the adding the smaller full linear connection modules into the top of the multi-attention layer, and so that they do not change significantly to the transformer module, but they adding some of the more trainable parameters to the structure. And usually this is like a very small parameters
没有，我只有50块钱，
overhead.
一个
But
打
it
50
tends
可以
to。be very good for the fine-tuning task as well. So to make the things more aggressive,
这个打50给1块钱给我充够，
having an LLM,
没钱了，
we assume to having the omnipotent models which can do
没
everything.
有，不要
So
钱，
currently,
你要
another
钱你
kind
不要
of
钱
the
就还给我。
parameter-free tuning is
死
just
鬼
kind of
畜
prompting.
啊！
And I believe Dr.
没
and
钱。
Dr. Hu have already mentioned some of the case studies of this. So prompting is kind of the tuning, but we do not to handle any of the parameters. We're just regarding as the inference data as one of the interactions to the models to tell them how to actually doing the prediction. And this is example for the prompts. So basically we have a task description and we tell them what we want to do to achieve in a model. And then we're gonna to gradually teach the language model the instructions, what we want to do and how they can get a correct solutions. So for this part, I want to give a quick example to see what is the prompt and what kind of the prompts can actually to do to unlock the possibilities of these large language models.
好了，我申请那个
So
助学
this is
奖学
the
金，到时候盖个
kind
章
of the
吧。
elementary
真
math
是。
problem, and basically we want to calculate a function, and this function is trying to represent the total cost when we're trying to building some of the solar power installation. So the thing is for this math problem, and
不
we
用，我
give
到时候跟老
the
师说，我这电
intentionally
剑
wrong
桥住了
answer
一个
to
月，
the GPT model, and we're trying to ask them to detect whether the solution
交也
is
只交
correct
一
or
半，
not.
都没出那里。
So as we can see, we have a additional square cost
是
of
啊，上次也是
$2.
这样子啊，
But
到
in
时
the
候我跟老师
functions,
说一下了。
we intentionally change it as 100. And then we ask the GPT model to see whether this solution
你
is
要是没
correct
钱
or
就别
not.
读了，他
And
妈
the
的，搞得
GPT
我烦
model
死了，
tells
操！
this solution is correct,
妈逼！
but actually it is incorrect. And as we can see, the GPT model, even though we assume they are omnipotent, but they are not.
叫你的臭嘴巴，他
These
妈
kind of
的！
very simple mistakes. So the things we want to do is to show how we can prompt to let the GPT model get the correct answer. So then we're changing our strategies to the GPT model is that we tell them not to giving their decisions at first. We give them the template to solving the problem by themselves first, and then compare their solutions to our given solution, and then trying to detect whether those two solutions are the same. If they're the same, they're gonna say this solution is correct. If they're different, we want the GPT model to see the original solution is false. So as we can see, we also give the same questions and also the student solutions. And the amazing thing is, so the GPT model, they can doing this math correctly by themselves. And then after doing a comparison with the original solutions, the GPT model can tell that the student solution is different from the original one. So they can give the solution that this is not a correct solution, which is correct. So this is one of the very simple example how we actually trying to do the prompting. And the prompting is just kind of the hint words. GPT model, they are very powerful, but they may not be powerful to digest every word and every mathematics at the first hand. And the thing is that we want to direct them step by step to do the things. And this is the very important techniques to interact with GPT model. And I believe this should be also one of the important steps current days to developing your inference data using those kind of prompts for your model development. And the last thing I want to mention is one of the work from our group that's different from those kind of hard prompts. We also trying to generating some soft prompts, which can significantly reduce the variance of these model prediction. So this paper we're trying to dealing with the medical notes summarization. So the hard prompts are actually generating from the LLM itself. But the thing is, we also introduce the informed sum loss, which is between the output summarization text and the input clinical text. And when we're trying to minimizing this loss, the soft prompts can be some of the vectors, which may not be comprehensible by humans. But when we appending these soft prompts together with the LLM, and the output prediction stability can be significantly enhanced. So the soft prompts, in short, it may not be something that easily to be comprehended by humans, but they can be very, very useful for you to have a better outcomes from your large language models. So yeah, this should be everything I want to cover. So any questions for this part? Well, if no other questions, I believe we should go to the break. Okay.
Thank you guys for coming today. So we already like past the time of the coffee break, so let's resume the session. So I'm Henry. I'm right now working in Apple as a machine learning engineer. So I'm in this session, I'm going to talk about the data maintenance and some data-centric AI benchmarks. Yeah, so let's get started. So in this session, I will basically come starting from like overview about the functional rules about how the data maintenance part and the benchmark serve as a functional roles to supporting the data-centric AI. And then we're going to talk about take a deeper look into the like how human understanding can be served as a functional support for DCAI, and as well as like how we evaluate the data quality and what's the impact of data quality, and also some example about like how people deal with the data quality for two different data modality. And finally, we're going to talk about like the benchmark, like from the model perspective and data perspective, and also some of the lessons learned from the existing benchmark. So as we have discussed before, like training data development and the evaluation data development are mainly as a main characters in the data-centric AI. But in addition to that, to develop a data-centric AI solutions, we also need some more like supports, because essentially we want to enable human awareness on the data, so that we'll be able to learn like how does the data look like and how we can proceed on our own like solutions. So especially first, the first one we can consider is like the human understanding. Like given the data sets, how do we know what kind of data we should? I mean, how do we know what kinds of knowledge could be included in these data sets? And also, what is the value of the data in terms of like developing the machine learning solution? And secondly is like given one data set, how can we know if the data set meets some certain level of the quality, and how do we do the quality control, and how those kind of quality metrics impact the machine learning solution. And third one is how can we really learn about like because given that the big scope of data-centric AI, how can we really learn about like which part is actually, I mean, what is the state of the art, and what is the pros and cons for each kind of like algorithm, and also like how can we really like do the comparison between each kind of like solutions. So to find out the understanding need in the data-centric AI, essentially, you can think about like from the machine learning build-up cycle. We're starting from like we have the input data. So basically, what we want to do is we want to understanding the whole data from input space to the latent space, and as well as to the output space. So the input space, what essentially you want to talk about like what, for example, we want to understand what is the data distribution, what is the data quality, and also what is the value of the data. And for latent space, mostly we are more likely to like creating some sort of like data from our heuristics, so that in this way we will be able to find out, to understand the model correctness, model robustness, as well as model capability. And finally, whenever we have a machine learning solution and we can do the prediction, and whenever we'll be able to produce some like evaluation results, then how can we really know about the result is correct, or what kind of feature selection can we find out from this output space is also a very important part. So essentially, what we want to answer the question here is like, how do we understand each step of the AI solution from a data perspective? As for the data quality, the reason why we need the data quality here is very obvious. Like if we, as mentioned from Dr. Hu in the first sessions, we are always, garbage in, garbage out. So if we have a very low quality of the data, essentially, even you have a very super strong model, it was still not going to yield a very good AI solutions. So here we want to talk about like how, we're mostly focusing on like how the data quality issues impact the machine learning solutions and how to address the quality problems on the fly with some examples. And finally, like for the benchmark parts, essentially we have so many different kinds of like solutions in terms of like model developments as well as like data development as well. So how do we really conduct the benchmark to better understand the latest progress? This is actually something that people are trying, at least starting from 2021. We are many people, there are increasing papers starting to study about what is the best pipeline or like the information infrastructure to really evaluate or to benchmark different kinds of algorithms. And also we want to talk about like what can we learn from the current benchmarks right now. So first of all, for input-based understanding, eventually, if we want to learn about like what is the data distribution or how can we really learn the knowledge from data distribution, actually, very recently we have there's a paper called the dashbots. The idea is we want to know about like how can we really visualize the data without human expertise, because essentially, for example, given a one data set, how can we know if we should use the bar chart, scatter plots, or different kinds of like plots? So without really the details of the business knowledge, it's very hard for us to really select a good visualization tools to create a good dashboards to study the data. So that's why like based on this motivation, this work, they propose a framework called automated visualization, and their goal is basically to create the visualization dashboard in the automatic way with the deep reinforcement learning. So you can see here, this is basically their framework. They formulate a dashboard creation as a sequential decision-making process. So in this way, for each of the states, they are kind of like defining what is the current dashboard or that's the visualization dashboard looks like. And then with this kind of given states, the agent network you can see here is trying to decide some action. For example, if we should change different kind of visualization methods, or we should add more columns, or we should remove some columns, or even like we should terminate the changes so that we can know like right now we're actually in the good position of the visualization. And to really trigger this whole automated visualization process, they actually define three kinds of reward. First, it's a diversity reward. Basically, the key idea is they want, given one data set, they want to have as diverse chart type as possible. So in this way, people can perceive more information from the outcome dashboards. Secondly, is parsimony. It's basically saying that we want to use as less chart as possible, because in this way, we can make sure that the same data set is not going to be visualized based on we're not going to be visualized from very similar charts in pretty much similar ways, in different ways. So a third one is basically the insights. So that's part, because that's a part that human expertise can still be injected, because essentially without the human expertise, it's still very, very hard to make the whole process become automated. So they actually provide a list of insights, for example, like some insight, for example, like if there are some like tabular for two columns, then usually if we want to know the trend, then we have to draw a line chart between from A column to B column, something like that. This kind of like insight actually provided by human experts, some visualization data visualization experts. So in this way, like what they can do is they can the whole agent network will be able to create a dashboard gradually that can fit the visualization experts expectation, as well as like create diversify and also parsimony visualization. So here is basically the the lower part, these two are basically the visualization they generated automatically. You can see with the inside of the horsepower for, I mean, this is basically the visualization for horsepower for the cars, for one cars. And this, the algorithm here, they can actually automatically find out, like, for example, whenever we're looking into some cyclinders, they should use some like bar plots. But whenever we're looking into more like a, let's say, horsepower with respect to the years for one kinds of like cars, they will be able to know like we should use the bar chart. So those are actually being automatically generated by the algorithms. So they also do some evaluation in their with the humans, around like 50 humans, and they do find out like overall people feel like the current the visualization dashboard that created by the dashboard is actually more preferable from the manual one called the multi-vision part. So that's basically the first one for input understanding. And secondly, whenever we know about like data distribution, we also want to know about, like, for the input space, we also want to know about if the data right now has a good value in terms of like training the model or having some more like knowledge within the data. So data evaluation is actually a very recent, I would say, very recent problems that are being proposed. And basically the ingredient given for this kind of data evaluation problem, including first, a data set, second, a learning algorithm, and thirdly, a performance metric. And the goal of the data evaluation is to evaluate the value of individual data instances of the data sets. So in this way, whenever we know the value of individual data instances, we'll be able to find out the core insight of the data sets, and further, and also find out which kind of the data instance within the data sets is more important, so that we can conduct some more advanced tasks, for example, like domain adaptation. Or sometimes we can also, if we know the core value of the data sets or data instance, then we can also filter out some of the corrupted data instances here. So very recently, actually the data evaluation, there's a one of the representative work I've been publishing on ICML before, is using the data evaluation with reinforcement learning. And the key idea is also to make the data sampling as a sequential decision-making process. So you can think about, given for during each of the iteration, we the data value estimator will be able to observe a batch of the training samples, and then the data value estimator will be perform a action, which is basically a probability distribution for sampling the given training data set, training data batch. And finally, to really guide this whole data sample selection, they use the loss on the validation data set for the predictor. So in this way, you can see if the data value estimator selecting a good select a good training samples, then basically the loss on the validation set is possibly to be lower comparing to the one that is not. So in this way, whenever we are able to down the training, the data value estimator will, when we input a new data set into a data value estimator, it will be able to automatically select which kind of which specific data instance should be the one that is more beneficial for training the data, training the model, training the predictor here. So that's basically the data evaluation for the input space understanding. And beyond the input space understanding, we may also interested in the latent space understanding, which is basically like how we can really find out the insight from a learned model. And recently there are many like papers or like works starting to study, especially for transformer based like language model, due to the complexity of the model. So it's one of the most representative work is actually this one. Is called analyzing the structure of the attention in the transformer language model. And this has been published in ACL 2019. And the key idea is they have developed 4 kinds of like heuristic scores based on the attention scores. So you can see basically the alpha here is the attention score that generated by the attention model. And then they did, based on this attention score here, they decide, they developed they try to evaluate the dependencies between the attention layers and also the dependency between each of the layers and the contents that input to the model. So they have these 2 kinds of like evaluation metric. And also they want to know about the knowledge consistency between each of the attention layers. So they developed they developed this kind of D bar alpha here, which is basically the distance, average distance of the attention layer, and also the entropy to evaluate the depth of the modeled relationship, as well as the knowledge dispersion with respect to different kind of layers. So based on this, the 4 defined score from this paper, they do find out like mostly in the very deep transformer model, they find out like there are mostly 3 kinds of like attention that we can observe. First one is called a focus attention, which basically try to focus on the current tokens. And the second one is the dispersed attention, which try to focus on only the previous tokens. And the third one is basically the long distance attention, which try to focus on the words in more like repeated phrases. So you can see basically the way they define this attention is based on the score that defines the variability, mean distance, as well as the mean entropy here. So based on their results, they do find out like they actually use that to evaluate 5 kinds of like language models, including like FLAM T5 and GPT-2, GPT-3, as well as some other, I believe there's some other like language model as well. And they do find out like some insight is like whenever we have deeper layer, the deeper layer usually have higher variability, meaning that there are more content-dependent relationships being modeled with the deeper layer. So it's not like so meaning that if we change the input data a little bit more, then the deeper layer will basically the one that is going to model this kind of changes. And second one is like deeper layer will have higher entropy, meaning that they are going to have a more dispersed attention. So if you still remember, the dispersed attention will focusing more on only the previous tokens. And the third one, here. And the third one is whenever we have deeper layer, usually we'll be able to identify some higher attention distance, you can see here. So higher attention distance meaning that the deeper layer is able to capture more longer distance relationships, meaning that they will be able to find out some more like relationship between 2 tokens that are become like far from each other. So that's basically about the latent space understanding. In addition to latent space understanding, we may also interested in like whenever we have model and we are be able to output the results and to do the prediction, how can we really understand the prediction performance metrics? So actually, like in Apple, there's actually a work that been published like recently on CHI, the conference on human factor in computing systems. They have tried to identify to understanding the performance metric for a real world scenario, because essentially the label that being defined for real world scenario is not only just 1 or 0 or just multi-class, because each of label could have more hierarchies or more like in-depth meaning with that. So how do we really map the confusion matrix, especially in this case, to the concept behind the training labels? It's actually something that very important to understand the models. So in this case, because real world, as I mentioned, real world usually comes with some hierarchies. So in some intuition from this work is that they try to understand the confusion matrix as a probability distribution. So how do they do that? It's pretty simple. They just do some like row-wise or column-wise normalization on the confusion matrix. So in this way, they for each of the row or column, it doesn't matter which way you do the normalization, they will be able to have the probability distribution for each of the class. And so with that say, if a label has some like hierarchies, for example, in the very beginning, we have class like lemon, lime, orange, or apple, but somehow lemon, lime, orange are actually belong to the citrus. Apple is belong to the palm. Then in this way, we'll be able to use the original distribution to make another original probability distribution to make another like conditional probability distribution between the hierarchies. So we'll be able to extend the original confusion matrix into more into more ways to visualize the performance matrix from different hierarchies. So it's actually a very simple approaches, but somehow they do find out like this kind of normalization on the confusion matrix is able to reveal some of the hidden confusions. Take one example here, like whenever we have a very imbalanced between each of the class, if we do some normalization on the confusion matrix and then we draw the confusion matrix with the hierarchies, we will be able to find out some of the hidden confusions. For example, like you can see here, these two part originally it was seems like it's not there's a lot of like effectives there, but whenever we do like normalization, then we'll be able to find out there are actually some of the confusions within there. The key idea is because previously we have a super imbalanced object counts between different kind of class, meaning that side like the checkbox here, this kind of specific class, because it has too many counts. So even before normalization, it's likely that we're not be able to sense that there are a lot of like confusion there. So yeah, that's basically about the output space understanding parts. Yeah. So for the next part, whenever we are able to learn about the data quality, so the whole data set from input space to the output space, the next thing we are more care about is like what is the impact of data quality. So recently, there is a paper talk about the effects of data quality on machine learning performance. They actually studied the data quality from 3 different dimensions. First is they call it as a pollution sophistication, which basically is meaning that the complexity of the polluted data instances. And the second one is a model complexity, which is basically saying that how the model how the capability of the algorithm is able to handle the low quality data. And the third one is a quality dimension, which is basically try to study the number of the quality issues in the data sets can how do this kind of like issues affect the machine learning solutions. So with these 3 dimensions, they actually define a desired data quality dimension or the desired data quality metrics. The first one is the consistent representation, which basically saying that the semantic uniqueness, we want to find out the semantic uniqueness of each features in the data sets. And secondly is completeness, which basically saying that we want to find a desired data set should have low missing ratio. And the third one is the feature accuracy, which find out like the low deviation of the feature value from the ground truth or from the perfectly designed data sets. And the next one is the target accuracy, which basically we want to have a data set that with a low deviation of the label value from a perfectly defined data set. And the next one is a uniqueness, which basically try to have less duplicated instances possible. And finally, of course, is the target class balance, so that we should have like some sort of a balanced class distribution. So based on these 6 desired data quality dimension, they actually create different kind of perturbation based on these 6 dimensions. So and then they study each of the dimensions that how do they impact on the prediction performances. So this is basically the result they do find out. This is one of the example they provided in the classification in the regression task, which is on the one of the publicly available data sets called predicted data set. The goal is trying to predict the credit score. And they actually use different kind of algorithms, including decision tree, logistic regression, multi-layer perceptron, support vector machine, as well as k-nearest neighbors methods. And you can see upon these 6 kind of methods, one of the most impact for is actually something like, for example, the completeness quality, because whenever the completeness quality become worse, the performance will actually drop more like drastically. But for example, for uniqueness quality, if they have some sort if we have like lower quality on the uniqueness, usually it is not going to impact a lot for training the machine learning model. And also for target accuracy quality, you can see here, if our label is super accurate, naturally, all of the algorithm will tend to fail when the quality of the target accuracy become lower. So they do have a summarization that because they have done this one on different kind of tasks. So they do have a summarization that mostly for both for all of the, for example, like classification tasks, regression tasks, and clustering tasks, the completeness, the quality of the completeness, and also the quality of the feature accuracy are mostly the two that will affect all the tasks in all of the models. So they have high effects. And previously, when people are thinking about like consistency, should be some issues for creating the I mean, consistency should be the issue for a quality data set, but somehow in their benchmark, they do find out like consistency will actually have lower impact to all three kinds of like tasks on those kind of classifier here. So that's basically the idea of the data quality. I mean, how we define that. And actually, there are actually more different kinds of data quality metrics that has been proposed in the previous 20 years or 30 years. But they are in this work, they only try to evaluate 6 of them that can be directly formulated as a mathematical formula, so that they can do the perturbation. Because some more metrics are actually more like abstract, for example, like reliability of the data resources. And this kind of like metrics should be, I mean, it's important, but it's very hard to quantify how they can impact our AI solution. I mean, yeah, how they can impact our AI solution here. So yeah, and to deal with kind of like this kind of impact on the data quality, one of the examples that we can find out in the natural language data is that people are trying to develop in different kind of data processing pipelines. So this data set here is actually being proposed in NeuralApes 2022. This is actually a new multilingual data sets for training a large language model. And in their data sets, they're actually using multiple data resources from the Hugging Face, Web Archive, GitHub code, as well as OSCAR. And you can see basically they have a lot of like different kind of multilingual data sets, as well as different kinds of like programming language as well. So what they have done here, because essentially there is a very challenging to truly align those kind of multi-data sources into a unified data set. So what they have done here is basically they develop a data pipeline starting from data merging to document cleansing and to document filtering. For data merging, they firstly try to do some like data pivoting to find out some of the like common shared data set or shared sources between each of the data sources. And then they try to merge different data sets by the latest version. And then after that, they try to remove some of the low instance of the some of the data sets with low instance of the incidence of the natural language, meaning that because sometimes if we directly take a look into Web Archive, it's kind of like crowd data sets from the web, then there are a whole bunch of like textual data that with a lot of like HTML tags, and that something is not desirable. They also try to remove the data set with high n-gram repetition, and also remove the data set with smaller than 2 megabytes. And after this one, they will be able to have a unified documents. So the next thing they have been doing is actually they try to do some document cleansing, for example, clean some of the HTML tags, and also try to segment or split the sentences, and also remove some references, as well as like using the TF-IDF based methods to do some deduplication between the documents. And whenever they clean the document, what they do next thing is they try to control the quality of the document, because essentially we don't want our document to have too much low quality things that will affect our large language model training. Some example, for example, like they try to compute the word repetition ratio and also some special character ratio. So they want some sentence with this kind of higher than those kind of ratios will be removed within the documents. And also they try to identify some of the flag words, because they mentioned that there whenever we are using the data set from web, there are a lot of like chronology words. So they also try to use these kind of flag words to compute the flag word ratio so that they can remove some like dangerous contents that may affect the large language model training. And yeah, and also they also include something like the perplexity value, that is basically to identify how many knowledge do we have within this kind of texture information compared to or texture data. Yeah, so that's basically the example of the natural language data. Another example is actually another like very recently being recent data sets that being published in the ACM measure of data, precision measure of data here. So it's actually a tabular data. In this tabular data, they actually try to extract a large tabular data from a corpus from the GitHub repository. So you can see this is basically the data processing pipeline, starting from very beginning, because essentially it's a GitHub repository data set. So they try to parse the data sets with some like to remove some of the bad lines and then realign some of the headers. Those bad lines and headers are basically the bad line here is just basically some like dangerous contents I mentioned, like something very similar to the flag words in the texture data here. And also try to realign the headers, because sometimes for GitHub repository, we may have some very similar repositories but somehow their naming should be similar and their content should be similar. They try to do some deduplication there. And later on, whenever they are able to do some like parsing for a data set, they do some table filtering to remove the tables from the GitHub repo. They remove some of the tables with extreme small size and the undefined columns here. So and then finally they do some like content curation to remove some offensive contents again, and to anonymize some of the tables, so that in this way the user information will not be leaking. And finally they do some like data annotation to do semantic and synthetic annotation based on the external source, for example DBpedia or schema that organizations. So you can see basically the whole idea is starting from the GitHub repository. They use they query some of the CSV file, and then they do some parsing on the CSV file to get up some of the undesired information, and then they do some content curation. And whenever we have different kinds of like attributes, for example like product ID, and also some of the keywords for each of the repository, they use the external resources to annotate the data. And that's basically about how they process the pipeline. And from their work, they do provide some like lesson learned from the data quality summary. That firstly, because as we mentioned, like in their work, they try to annotate the data from both semantic and also synthetic ways. And they do find out like using the annotation with the semantic meaning of the columns actually leads to more annotation per table. So I mean, it's not necessary to be the most meaningful, but it just have more annotation, because they say like using synthetic one will have more like missing values to do the annotation. And secondly, when they try to compute, secondly is like they find out like whenever we have the data, we have the table ready, they actually somehow make the whole table become, make the the whole annotated tables, let's say for each of the rows, and then they'll be able to compute the cosine similarity between the different kinds of annotation. For each different kind of annotations between the rows. So in average, if the cosine similarity has higher, meaning that they have a higher confidence for the annotations. And the thirdly is that they find out like comparing to the other data sets that have been provided previously. Let's say previously there is another data set that is also using the GitHub data, but they somehow have different kinds of data processing methods to yield a final tabular data. And they find out that whenever they are training the model with these two data sets, they find using the Git tables that they provided has a better predictive performance than the baseline, which is basically this net here. So the whole point of this part is that we should the whole point of this part is that we do they do find out like even though we are having the same data sources with different kinds of like pre-processing part, actually it will lead to a lot of like different results on the model training part. So we should somehow like focusing not only on the model training, but also on how do we process the data. That's probably the most important part. That's basically the conclusion from them if they find out. So yeah, so basically after all this like data quality parts, the next thing I want to talk about is basically the data-centric DCAI benchmarks. So as we said, like we already have the quality, we know how we do the training data development, inference data development, as well as like how do we control data, and also how we really do the data understanding parts. Benchmark is also a very important part, because without the benchmark, we can never know about what kind of methods is more effective, or not necessarily effective, but more suitable to our own scenario. So actually, right now there are actually two of the most largest benchmark we can find out in the academia. One is called the MLPerf, which is basically try to do the benchmark from model-centric. And another one is Data-perf. It's basically we want to do the benchmark from data-centric. So fundamentally, the differences between the MLPerf and Data-perf is that the MLPerf is actually more like application-driven. And also they have more computational focused, and as well as like they have an assumption that the input data must have a good quality. So you can see right here, this is basically their like some sort, I would say like some sort of like a benchmark framework that they are kind of like a from top to bottom, starting from application until the hardware target. All they care about is about how do we do the computation. For example, what kind of hardware should we use? What is the operating system? What kind of compiler? What kind of library as well, framework, as well as what kind of model we're using. So nothing is about the data sets. But for data-centric benchmark and for Data-perf, we are more like an application agnostic. And also we focus more on data quality, and there is no assumption on the machine learning models. So in Data-perf here, their structure is like you can see the model part here is just being fixed. And mostly they care about is like they try to changing different kind of data processing methods, data augmentation methods, different kind of representation selection, data quality assessment methods, and data acquisition methods, as well as data cleansing methods. So that in this way they find out by fixing the model, we only changing how we process data, which kind of like data pre-processing techniques can actually lead to better performances. And this kind of benchmark, these two benchmarks, there is no who is right, who is bad, or something like that. They are just complementary to each other. But recently, because model-centric benchmark has been developed so well, starting from very long time ago, but data-centric benchmark is just the starting point here, because essentially there are still not much work on how do we do the benchmark on data from data-centric perspective, and also there are still no much about like unified studies on how do we processing the data. So in our survey paper that we provided, we actually tried to sort out all of the existing benchmark we can find out right now. And starting from training data development to evaluation data development and to data maintenance, as well as like find out unified benchmark, you can see basically right now is like we can find out, first of all, data-centric AI is essentially a interdisciplinary efforts, because if you take a look into the domain here is like, it's not just we AI or data mining people are doing data-centric AI, but also some people from medical domain, biological domain, as well as different kind of cybersecurity domain. They are also working on this area. And secondly, when we take a look at all of the benchmark papers, we also find out like the popularity of the data modality for benchmark is still starting from tabular, and then image data and time search data, and then audio, and finally is the graph data. And the key idea when we take a deeper look into that is because we do find out like graph data is just like an emerging topic from recent years. So there should be some more like space for us to improve for that part of the benchmark. And finally, is like obviously when we take a look into the benchmark, we can find out exhaustive search. After our exhaustive search, we do find out like mostly the benchmark are still focusing more on the training data development, and then the maintenance, data maintenance, and finally the data evaluation. So this actually prompts us like more and more focus that we actually should be calling more actions to try to benchmark for either maintenance and evaluation, because right now people are still focusing more like data augmentation. So you can easily find out a lot of like benchmark paper for data augmentation, data labeling, something like that. So, but still, these two parts are still very important. So that's something that we may want to take a look into that more. So, yeah. So this is basically about my session here. So I'm so let me know if you have any questions. Okay, good. Okay, so next one, let's welcome Siray for the next session. Okay.
Hi everyone, I'm Siray, third-year PhD student from Texas A&M, and thanks for Dr. Zhou for helping preparing these slides for this data bias and fairness section, and I will present this section. So for this section, I will introduce three subsections here. So the first one is we will talk about the distribution shift in the data, and the second one we will talk about the bias and the fairness problem from the data perspective. And last but not least, we will see what will happen when the fairness happens under the distribution shift. So let's first take a look at what is the distribution shift. The distribution shift happens frequently because of in the real world data scenario. For example, the different positions, different hospitals, different experiments, and also different time periods, and also different devices to collect data. So the distribution shift is actually versus to the ID assumption, which let's take the image, for example. The distribution shift can indicate the style of the image is different when we do the training and the testing. And the ID means the style of the image is actually the same from the training distribution and also the testing distribution. So there are four categories of the distribution shift that we concluded. So the first one is the covariate shift, which means the shift happens in the input data. And the second one is the label shift, which means the the distribution shift happens in the output data. And the third one is the demographic shift, which is the distribution shift that happens in some sensitive attributes, for example, the gender or race. And also the last one is the compound shift, is the mixture of different kinds of the shift. And our goal in the distribution shift field is we want to maintain the performance when we transfer when we test the model on the domain shift data compared to the training data. Because as we know, when the distribution is different from the training and the testing data, so the performance will usually drop. So there are two categories, main categories of the domain generalization method, which can be used to mitigate this performance degradation when it meets the domain shift. So the first one is the data manipulation, and the second one is the representation learning. So the data manipulation is a kind of data-centric method, which is the focus of our talk here. And the representation learning method focuses on more of the model level. So the there are two subcategories in this data manipulation method. The first one is the data augmentation, and the second one is the data generation. And we will introduce these two methods in our following slides. So the data augmentation's core idea is we want to create the out-of-distribution training data based on the transformation of the original data, so that the model can see can learn from the out-of-distribution data when it's trained. And the second one is the data generation. The core idea is we want to generate diverse training data to help the model to be generalized across different domains. And for each categories method, we will introduce one representative work. So for the data augmentation method, we will introduce a work called domain randomization for transferring deep neural networks from simulation to the real world. The core idea of this paper is we create diverse training images from the simulated environment via domain randomization. And the task here is the object detection. So in this paper, the authors propose 7 kinds of the domain randomization method to transfer the style of these images. And from the experiments and the ablation study, we have several key findings and observations. The first one is we find that the efficiency of different randomizations varies for different target object, which means when you want to train a general model that can be that can have high performance across different image tasks, you need to have the combinations of these 7 different kinds of the randomization methods. And the second observation is the number of augmented data is crucial, as shown in this figure 4. So in this figure, we can find that when we increase the number of training augmented training examples, the average error or loss is decreased, which means the performance gets better. And also we have 2 extra observations for in this paper. So the first one is if we just adding some noise to the simulated images, it's not that working. And the second observation here is the textual randomization shows effectiveness with increasing amount. So for the second categories of the data manipulation method, it's the data generation. And here we want to introduce a representative work. It's called domain generalization with mixed style. So the core idea here is inspired by the specialized the characteristics in the computer vision task. So we have 2 observations. The first one is the visual domain is closely related to the image style. And the second observation here is the image style information is usually captured by the bottom layer of the CNN. So the goal here is we want to generate normalized style images for training a generalized model. So the core techniques of this mixed style paper is the authors want normalized styles from different domain images of the same class in the latent space. And we have 2 kinds of the shuffling of operations. The first one is if we know the domain label, and the second one is if we didn't know the domain label. So and these 2 operations is both implemented on the batch level. So the reference instance batch can be obtained by these 2 operations. So with this technique, we have some significant improvements compared to the baseline method. So we find from this table 1 that the mixed style shows promising efficacy on the image. And the second thing is the mixed style is hard to be used for other types of the data because this idea and this paper is inspired by the image and also the computer CNN network. So with this kind of motivation that we find here, the idea relies on the characteristics of the CNN, which we may think that can we develop, what if we mix other kinds of the data besides the image? So here comes our work that's called graph augmentation via graph mix-up. So the challenges here in this task is we want to do the augmentation in the graph level for the graph data. So one kind of the graph augmentation method is the mix-up. That is, we want to generate the new graph, new data from the original graph by combining them together. So, but the graph is not like the image. It's very hard to align. It's very hard to be combined together because they have different number of nodes. And also, even if the graph has same number of nodes, it's very hard to align these two graphs because of the because there is a node level correspondence. So how can we mitigate this challenge? So a naive or intuitive method is, although the graphs, the original graphs are not well aligned, the learned representations of two graphs are well aligned and can be interpolated directly. So a straightforward way to apply mix-up to GNN is directly mix the latent representations of these two graphs. So further on this work, we may ask, can we directly mix up two original or raw graphs that at the data's level? So here is our ICML work, and it's called the G-mix-up, the graph data augmentation. As we know, the real-world graph within one class can be generated by the same generator. For example, here we have the graphs that have two clusters, but they are different graphs, but they are all have similar topology from the high level, because we have two clusters or 8 clusters in another subgraph. So we may ask, can we just have a graph generator to generate all kinds of graphs? So we propose a concept called as graphon. So graphon can be thought as a probability matrix, where each represents the probability of age between two nodes. And the original graph may be different, but their graphons are the same or are very easy to align. So we just mix up the generate all the graphons of these original graphs and mix up the graphons of different classes, and then we can generate the synthetic graphs. So in the previous work of ICML, we still have some assumptions that we can use graphons to generate the every graphs, but can we have some method that can be more flexible to mix two graphs together for the augmentation? So here we have another work, is called graph mix-up with soft alignments. And the core idea of this paper is we have an assignment matrix. So what does this assignment matrix do? Here we can let's take an example of the graph G1 and G2. So G1 we can find that they have 5 nodes, and the G2 have 6 nodes. So we want to align them together. And here the assignment matrix is actually a 5 multiplied 6 matrix, which is the corresponding numbers of nodes in these two graphs. So this matrix indicates the probability that this nodes correspondence between these two graphs. So if we can learn this kind of assignment matrix, which means we can use this matrix to transfer one of these G1 or G2 to be easily aligned to the other one. So this is the core idea of this paper. So the first step is we do the soft alignments, and then we transfer this, for example, here in this figure, we transfer the G2 with this assignment matrix into another graph that can be easily aligned to the original G1. And one of the advantages of this method is it can preserve the cycle motif in the original graph. For example, we have the experiments that on the left figure is the original graph data, and if we just do the random mix up, we can find that it lost the cycle motif in the original graph. But if we use our method, the S mix up, we can preserve this cycle motif, which is a very important subgraphs in the original graphs. So from the experiments, we find that the S mix-up can improve the generalization of graph neural networks. Here we can find that when, especially in the data set of IMDb, these two IMDb data sets, we can find when the training app reaches the 100, the other baseline method, they will be overfit, and the loss will increase from the 100 epochs. But the original, the orange curve, which is our method, it can still be converged. And after we have seen some works from in the domain shift or distribution shift area, let's talk about some bias and unfairness problem from the data perspective. So the reason of unfairness and why it is very hard to address this bias problem, we concluded as 3 points. The first point is the data set itself exists bias, and the model training can amplify this model bias. And the second one is the black box nature makes it very challenging to detect the model bias. And the third one is the interpretability is a useful tool for help us debiasing the model. So here we want to introduce. So there are 3 categories of the mitigation methods to help us reduce the bias from the data perspective. The first one is the pre-processing method, and the second one is the in-processing mitigation method, and the third one is the post-processing method. So the pre-processing method is more focusing on the data perspective, it's more data-centric, and the in-processing method is usually we add some fairness regularization when we do training of the model, so it's more like on the model's perspective. And the post-processing is we have already trained the model, and we have and we just directly calibrated the output of the model. So here we want to introduce a work. It's called automated fair graph augmentation, and it's a debiasing method from the data's perspective. And this paper's goal is to we want to use the data augmentation method on the graph level to improve the fairness performance of the graph prediction task. So here we have 2 optimization goals. The first one is the informativeness, and the second one is the fairness. And the pipeline goes like this: we have the original graph, and we want to learn the augmentation method that is applied to this original graph to improve the prediction performance. But how can we learn this augmentation strategies when we do the training? So we have 2 MLP, and these 2 MLP is applied to different levels of the graph. As we know, the graph consists of 2 levels. The first one is the node level, and the second one is the edge level. So these 2 MLP do the perturbations or the feature masking on the edge and also the node level to do the augmentation. And this augmentation process is learnable. So if we want to learn this process, we need to have some learning objectives. So here we have 2. The first one is the maximize agreement between the original graph and the augmented graph. It's a classical loss function or objective that we want to learn the suitable or powerful augmentation method based on this original graph. And the second one is we added in this paper that we used the adversarial learning as the learning objective to improve the fairness when we do this augmentation process. So in this paper, we have 2 kinds of the augmentation module. The first one is the edge perturbation, which is removing or adding the new edges or the existing edges. And the second one is the node feature masking, because for each node we have the representation or the original features, and we just set some values to 0. It's like the masking these features. So we compare to the baseline graph augmentation or regularization method, and we can find that on these 3 benchmark data set. Here the ACC means the accuracy. We can find the higher the better. So we can find the accuracy we can achieve competitive accuracy compared to the baseline method. And also here the delta DP and delta EO is two commonly used fairness metrics. So the lower the better, the lower means the less biased. So in this paper, we can find our method can achieve significantly smaller bias compared to the baseline method, the baseline augmentation methods on these three benchmark. And also we can achieve a good accuracy and fairness trade-off, which is presented in this parallel from curves on these three datasets. Okay, so we have seen the what some works in the distribution shift and also some works in the fairness. So let's see what will happen when the fairness meets the distribution shift. So here we have the findings that the fairness is not transferable under distribution shift. Means when we train a model on the training set or training distribution, it is fair. But when we transfer this model from the training distribution to the testing distribution, the fairness metrics or the fairness performance is not guaranteed. So why this will happen? The main reason is the demographic shift, because in the previous works we introduced, we mainly focusing on the prediction performance, and we usually pay less attention to the fairness metrics when we meet the domain shift. But the demographic shift is also a very important or very common distribution shift that happens in the data. So with this demographic shift, the model is very hard to maintain its fairness metrics. So we may ask if we want to maintain this fairness metrics under the distribution shift, what kind of conditions should we meet? Let's take the DP as an example. The DP is the prediction is the commonly used fairness metrics, which is short for demographic parity. And so first we want to make sure that our model has a low DP, which means it's less biased at a source domain. And then when we transfer this model from the training distribution to the testing distribution, if the prediction performance of the model is similar or is close from source domain to target domain, which means it can indicate that this low bias or this low DP can be maintained. So that's what we expect, the low average prediction gap between the source target dataset at the same sensitivity group. So with this very simple intuition that we expect from the fairness transferred from the source domain to target domain, here we want to, before we come to the technical detail of this work, we want to introduce some intuitive method that inspire for this piece of work. So the first is the rethinking of the distribution shift. As we know, the distribution shift happens in the data, in the original data, but it's the real world evidence. It's what we find from the data, and we may ask, can we simulate this process when we pre-process the data, and we find that it's achievable. For example, we have introduced the data augmentation, the data generation. It's like data perturbation can simulate this kind of the distribution shift that can guide the model to be generalized trade. And we may step further that can we do this from the model's perspective? Can we directly perturb the model weight to simulate this process that happened in the original data? So we have already proved that we can use the model perturbation to simulate the data perturbation, and then data perturbation can also be equalized to the original distribution shift happening in the raw data. So that's our core idea inspired this piece of work. So so how can we achieve the low prediction gap as we just introduced before for each demographic group? Here we want to introduce, first one is the weight perturbation. The weight perturbation in this work is achieved by the recent work is called SAME. It's short for sharpness aware minimization. And it can be accelerated with two forward and backward propagation. So the loss function for this work consists of several parts. The first one is the classification loss, which is a traditional or conventional loss function in most of the classification tasks. And the second one is the low DP on source, which is a regular fairness organization that is added to the model training. And the third one is the low prediction gap, which want to guarantee the model have the close prediction performance for the same demographic group in the source domain and both the target domain. So from our experiments, we do two folds of the experiments. The first one is the synthetic distribution shift. We find that our model can have low prediction bias at low intensity distribution shift and is comparable at a high intensity distribution shift. And also we conduct experiments on the real world distribution shift. For example, the temporal shift and also another kind is the spatial shift. We can find the performance of our model is also competitive in these two kinds of the real world distribution shift. Yeah, thank you. That's all. Okay. Any question? Okay. Yeah, and let's welcome Dr. Gao for the last part. Yeah.
Okay, so let me check my use this pointer. Cool, works. Thanks everyone, and thank you for attention and thank you for staying with us so long. So we have been discussing about the data-centric AI for data training, data inference, maintenance, benchmarking, fairness, bias. Now, are you ready to take some real-world examples in industry? My name is Huiqi. I work for Airbnb, and but on purpose of today's presentation, I will mainly talking about the general trend and direction in the industry. So instead of like going to very specific example of Airbnb or other company, and I hope this can shed some lights. And I also wish that everyone will enjoy the rest of the journey of this talk. So now staying with me, let's get started. Where we are talking about the data-centric AI, most of the time we are thinking about how to build high quality data, how to build a good foundation of the data. For what? For applications, to support better applications. So this is where we are going to get started from application. And from all kinds of applications, I'm picking search and recommender systems because one, a whole universe is kind of full of search recommendations. We use search recommender system to looking for information. We look for food, friends, jobs, news, sometimes even ads. And when you go outside looking for rides, we're looking for rooms to stay. So it's pretty much like everywhere. And while we are talking about the search recommender systems here, typically there are three categories. First, traditional web search. You can use that to search for all kinds of information, like Google, Yahoo, Bing, Baidu. The second type, online social networks. So basically, the search recommendation can also leverage your social networks. And we still use that to looking for either virtual content or what kind of other information here. Again, like jobs, looking for food, looking for ads, news, but under certain assumption of your social networks. For example, maybe you are interested in something that your friends are also interested in. The third category, that is, oops, where is the third one? Okay, here, online e-commerce. And in addition to those social engagements, we generally very care for online social networks. For example, showing you something, you click that, and you engage a comment like that. Online e-commerce marketplace focus more on the actions after that, whether you are going to purchase it or not. And it's not like most of the time the social engagements can be free. You can feel free to click 100 times, but the purchase, you're going to pay something for that. So that will involve some careful thinking. And these three categories pretty much cover most of the search recommender system that we are using, we are talking about in industry. The last one, the typical examples are Lyft, Uber, Airbnb, Amazon, eBay, you can imagine that. We are talking about the data-centric AI. Now I'm introducing the search recommender system with so many different categories. What's the common part? So let's first take a look at the common structure, how the data flows into these systems. Three key elements here: query, item, and a user. In the search scenario, a user searches for items with a query. And in the recommender systems, the system proactively recommend items to the user. So this search part is very specific to query. And but no matter what, we need to understand the query, understand item, understand the user, and go to the next step, candidate generation. Why do we do that? Because many of the time, the item pool is very large. It can be millions or billions of items. There's no way for us to directly send a large list of items for ranking, which is nowadays using very sophisticated algorithm, deep learning algorithm to do. We need to handle the online latency. So candidate generation is a way for us to reduce the candidate set from millions to billions to maybe a few thousands. And then we are confident to send to the ranking, making a ranking process more efficiently and return result to the user. Now, excuse me, about the process. There usually can be some online assistance like autocomplete, smart compose to help guests make the search and recommendation more smoothly. Without losing any generality, I'm going to focus on the ranking part because first, this is still the foundation of many of the components in search recommendation. And the second is even we are talking about online assistance, like autocomplete something, in the end, it's a ranking of like queries or ranking of other items. So we are going to focus on ranking. And I believe most of you are already familiar with the ranking. What does ranking do? We have a user, we have an item, we have some context. Now we want to predict how likely this user is interested in this item, such a prediction score. And we are going to do this for all kinds of items towards this user. Then we are going to rank the top items here just to show to the user. Okay. And in order to do that, we want to capture user interests from their user features, mostly from profile or behavior. And the same thing for the item. We want to get the features from user items, attributes, and past engagements. There are plenty of information for the context, like a query is context information, device information, time information, weekly, weekend. These are all counted as context. And now what do we want to do here? In order to build such a ranking system, we need to build a lot of data flow pipelines. There are typically a few pipelines here. One, offline wise. We need to look at how to generate the offline features. And we need to generate offline training testing data, also build the model training pipeline. Online wise, we need to generate online features and also serving for the ranking models for online to generate ranking results, right? So then let's take a look at, now we narrow down to the search recommender system ranking part and these important flows. What if you put them all together? What is the basic data architecture looks like? Right, that's the next step. By the way, is the voice okay? I feel a bit chilly here. I still have wear a hoodie something. So okay. Let's starting from the user. User comes to this website search recommender system, issue a query or without query if it's recommender system. Now this is making request. I want to see something. Then the system is going to first of all fetch real-time features, which will be used to generate online scores. And this request also make sure it goes to the online scoring ranking function to make sure this is at headings here, say, hey, I want to generate a score. And it will also use the real-time features. And with that, it will generate a ranked list of items, send it to the user. The user is going to engage with that. Now we are going to talk about engagement later, but you can imagine, you can click, comment, like, purchase, whatever things here. The whole part is online. And all the online part, as you can see, the engagement of these things, they can be logged. And the logging data we're passing through, stored somewhere. And we are going to use this logging data to, first of all, generate labels for our training model and generate features. And it is worth noting here, most of the time, the feature generation comes with a key component called a feature generator, because this generator will not only generate an offline feature, it also needs to generate an online feature. And for those that can be computed, That's easier. We just store them in an offline storage and support for the online scoring. Now, no matter whether the feature can be pre-computed or can be real-time generated, the full set here, actually here, the full set here, no, it's here, will be used to generate our training and testing data, and then used for model training, evaluate the best model, deployment, and support for the online scoring. And the whole part is for offline. Okay. Next, I'm going to just dive deep into a few components here, from logging to label to feature, and just to shed some light about what are the challenges and what's the general practical lessons learned from there. So starting from the logging, we have talked about like a user can engage with items online a lot, and to, as we said, we are going to log this information. What does it look like? Like, imagine you come to a search recommender system, you see there are like 5 items here, ranked by their ranking score. Some of them, you are going to click on that, get into their landing page. Their landing page can contain more detailed information of these items. For example, you can have their, you can click on their images on their landing page. You can change their product settings to get a different price. And after that, you may make a decision, say, I'm going to purchase one of them. Then this goes to the convert. But after that, you may regret, feel, no, this is not what I want to cancel or return that. The whole process comes after user has seen until the actual actions can be logged. So let's take a look at what will be logged exactly. First, user context. What is the query user has been pushing here? What is the user context like about their real-time profile? Anything changed there? This is something usually we don't get offline. Secondly is this ranking context. While we are showing a list of items to the user, what was the model behind that? What was the feature behind that? And how this ranking score is computed in this way? Any tuning we have done, this needs to be logged. And then the whole engagements needs to be logged. So there are things we do not need to log in general. One is a user profile, another is the item properties, because usually they are static. You don't have to do it online in real time. You can always access it somewhere pre-computed offline. And just to come back to our discussion about the different categories of search recommender systems here, usually for web search and online social networks, we go from view to click, and most of the time go to the landing page engagement. That's pretty much what we want to optimize. And for the ads and online e-commerce, we need to go a bit further, how to convert and how to reduce the cancellation rate. That's pretty much, yeah. But no matter what, it shares a similar logging system. Yeah. So features is usually straightforward. You have user raw data, context raw data, and item raw data, as we just discussed. You want to convert them into features. And a general principle is maybe I should stay a bit away here. So a general principle is we want to build a centralized feature transformer. So the transformer either can be part of the component in your whole neural network model for training, or it can be separate process, help you to the bucketizing, or help you to do aggregating different features, like how many times you clicked on this item before. Now, but it needs to be centralized. That can be easy for maintenance. And of course, so we want to model capture user interest, item properties, and the product context of that, then goes to the labels. Here, I think most of the audience here must be very familiar about how to do the label. Let's use like a news feed as an example, right? Whether you are going to click on a news based on whether you have seen that. If you have seen this news and you click it, it's positive. If you see that, but you don't click it, it's negative. That's for general CTR prediction. But how about for this long chain of engagements from click to landing page engagement to purchase request, purchase, and cancellation? Let's say we want to model this, we want to model probability of purchase given the user has seen this item. How can we do that? An intuitive way is, again, if the user has seen this item and purchased, it's positive. But if the user seen this item, no purchase, this is negative. That's the most intuitive way to do that. But is this accurate? Let's think about it. What if you have engaged with this item before your purchase? You look at their landing page. You're even almost going to purchase your input to your bank account, but you just didn't do that yesterday, and you did it today. Then for yesterday data, are we going to consider this as a negative signal to the model? Likely not, because this will confuse the model. The user did show the interest to that. It just didn't finish the purchase process. But then how can we do that, right? Can we say this is like perfectly positive? Maybe not. What if this has happened like 1 week ago? It's already passing like I don't know how many days. So maybe already losing the interest, or the interest has shifted, although they have still purchased the item in the end. So I'm not going to talk about the detailed like solution, how to do that, but there's a general technology called label attribution. The idea is what kind of action should also be considered as positive or certain weight of positive if the item has been purchased in the end, but was engaged in the past. How many such action in the past should be fetched to better label them? Yeah, and it turns out that this is actually very powerful in terms of general like a binary weight of labeling. And another way is if we look at all these different losses, we can actually model at a different stage, CTR, CVR, purchase cancellation given purchase, and we can put them together as a single model with multiple losses. Okay, now we talked about the feature label and logging. Before we go to the technical like a modeling part, I just want to highlight something here. With such a data system connecting offline and online, it is very easy to get into online-offline discrepancies. So example is how to generate the testing data. The general principle is, yes, we need to have a good representation of the training data, that's of course, to reflect the real traffic. We need to consider weekend effect, seasonality, different big events, and we want to avoid the information leaking. We never want to predict the past with the future information. That pretty much corresponding to here, right? Now, what else can cause online-offline discrepancy? One is we roughly discussed the feature generation discrepancy. Here, we are using the same feature producer to generate an offline feature, which is for model selection and training. Also use that to generate an online feature, which is direct consumed for scoring. What if the feature producer for these two components are different? Would it be a discrepancy? The answer is yes, right? Yes, but you may ask like, hey, come on, how come you are going to build two different components for offline and online? It must be the same component, right? So there are certain hard limitations in general when you build a search recommender system. For example, offline, when we train a model, usually we use Python, nowadays right, with TensorFlow Python, and it is also easier to build some features with Python. But online, many of the serving stack is on Java. So one may need to translate the language to Java, implement it again. But these two different implementations based on different languages, sometimes even based on from different people to implement, they can have certain chance that get into some rabbit hole. It just cannot figure out like why at a certain circumstances these two things supposed to be identical risk, but it just generate different things. Yeah. So another thing is about the model scoring and discrepancy, scoring discrepancy here. So basically around here, you have the offline evaluation to generate, to pick your best model. You have online scoring to get the actual score. But what if these two scoring functions are based on different libraries, say different TensorFlow versions? For example, if you use bench normalization, you probably will sense that with different TensorFlow versions, you will get different distribution. And that usually will cause a lot of online challenges where you just have no idea why suddenly the model is proposing something different, or even didn't notice that. And the last one is called actually it's like more like data bias. Here, whatever logging data we get for train our testing to generate our train testing data, it is from the logging from the last model. So that means if your last model never recommended something, then that thing, even it is very good, it doesn't get a chance to get it flow into the whole system. The model will just consider either ignore it or just consider it as negative because there's no engagement with that. But it's not fair, right? So how can we do that? How can we ensure those items silently hidden by the previous model for whatever reasons can still have certain visibilities here? So we can have a more robust training and testing data, enough coverage. One way is we can do exploit. Another is there are many other ways. So you can also use some kind of thing called a random bucket. But basically, we want to get out of the rich get richer, poor get poorer scenarios. Okay. Yeah, now pretty much before we go to the actual model training stuff, I just want to highlight a few things. The various data types in search recommender system. You have structured data is most commonly seen. Like this is a flyer I get from KDD website. It's more like an activity recommendation. Looks like there's a very nice quiz around here. So you can see the price, date information, location information, and also there are text data, comments here. Some maybe there's no review, but in other places maybe there be reviews, descriptions, and a nice picture, image, video, nice picture, very nice total picture. And I engaged with that. Actually, I purchased the tickets for that. So these are the information you can get different types of data by looking at this activity recommendation. Although technically on KDD website, there are only 2 activities recommended. So it's not very competitive to get a user purchase that. Now, the thing is, we can always put everything together and train a bigger model. But is it necessary? For example, if we starting from scratch of the text data, image data, just from random embeddings and go through the whole ranking model, most of the time it's very hard to converge. And also there's no need to do that. There's better ways, pre-train a model. That's how people usually handle such multimedia data. And with so many different versions of large language models here, and it becomes such a good practice to handle multimedia data and treat it separately as a pre-trained model. Now, of course, the usage can be different. First of all, training large language model, for example, like text model, the focus may not necessarily towards a certain ranking perspective. It can be look at how to optimize the semantics behind that, how to predict best predict the next word, how to actually predict the missing keyword or phrases. And with that, we can fine-tune it in a task-specific model. Here it will be a ranking model, which would focus on optimizing NDCB, NDCG, and AUC. Now, another practice is if you have very specific domain data, say this activity recommendation, you have very nice total picture and very specific semantics, you can actually train your own large language model with your domain-specific data. And although nowadays, I think there's a widely used large language model should already be able to capture those information. But if you have such a need, you can do that, because another benefit is then you can control the structure and the complexity of your own large language model. You don't have to go with 20 layers, 100 layers. 3 layers could be enough for your data. And then again, use that to fine tune in your ranking model, say. So I just gave some example about how this ranking pre-trained model can be used in ranking. Say, let's just use text as an example. You have a lot of text data, and we can classify them into source fields and target fields. The source fields can be on the user side, like users' comments, users' review, user query, and the target fields could be on the item side, title, description, all these things. And then, of course, we have pre-trained a large language model, so we can generate their embeddings for each field here. And because we have a source field and a target field, it's very natural for us to hit a match between them to get a certain similarity here, score here, to represent their whatever their matching score. And usually for the ranking model, we have the handcrafted features already in the system. So put them together and then go to a few layers. Then we can optimize by learning to rank loss, whatever point-wise, pair-wise, and listing-wise. Right. So this is example previously published in published as for DText, how to use text language model to improve ranking with all kinds of fields. Now, here, I think one thing I want to highlight is while we are talking about a large language model, fundamentally, we are dealing with sequential data. So text is a sequence of words, and image can be considered a sequence of pixels. Video is a sequence of images. What about another sequence of data? Engagements, right? The user can hit a lot of items with different interactions: view, click, purchase, reject, cancellation. This sequence itself can be used to represent the user's action semantics. Yeah, so it seems pretty straightforward you can form whatever sequential chain of this user and treat it as a sentence and feed into large language model to pre-train that so that you can learn all the engagement context. That is indeed one direction to go. But the challenge is also pretty tricky here because engagement sequence and word sequence, they are still different. For word sequence, usually it has a natural meaning and a forward semantic meaning. Like if I'm talking about we are giving a tutorial at KDD. If we look at it as the engagement sequence, I probably look at this word is like I'm giving tutorial at given KDD. Things like, because engagement wise, it's very easy for people to go back and forth. It's kind of repeating the same word again and again. You have no idea why it is talking in that way. So I think it's probably mine. Just to give me a second. So engagement sequence is containing a lot of noise, and we usually need to do a lot of data processing to make sure it is ready to be used. Otherwise, we'll have to figure out how to better change your large language model changing structure to handle this noise data, which is usually does not exist in text data. So just one highlight here. Okay, we talk about the pre-trained model. What about the data dynamics? While we don't have to put everything into one model, but some of the information can be pretty dynamic. So they may on the different updating frequency. Let me give you an example of such feature. We usually talk about like a global personalization stuff. And when we look at the data from a user feature, we can use their profile, we can use this past behavior, like all these information we use. What's the purpose? It is trying to best represent this user, the interest, right? But if we look down into all the information, what is the feature in finest granularity that can represent this user? Will be this user self. And what if you just use the ID of this user to represent the user as a feature? And the same thing for the item side. In addition to all the item-related attributes past engagement, what is the finest granularity to represent the item would be the item's ID. So we can also use the item ID to represent this item. And then you can see that by adding these two ID features, it exponentially increases the training data. Because for some of the conceptual conventions, you can easily get hundreds of millions of user ID or item ID. And this is not even to mention how you cross this ID feature with other features. Then how to train them efficiently and how to serve them efficiently becomes a challenge. And of course, the reason we want to handle this is because, first of all, it is helpful. And this is actually one of the most popular practice in online social networks. Second is because you are dealing with ID features, when whatever changes here, it changes immediately. So we have to capture the dynamics of this ID distribution shift, which means we cannot wait for like months to retrain that. Now, so a typical practice here is you have global model with a bunch of personalization model. So the global model can contain most of the stable features, whereas the personalization model can contain the personalization part. For example, each user can be trained as a single model under this user ID. And you can imagine because only this user ID related data will be used to train the corresponding model. It won't be a lot of data. Only this user ID related data. So eventually you will have a global model with maybe hundreds of millions of personalization model. Each model can represent a user or represent an item or both. Now, and why do we need that? Like when should we use this kind of structure? First of all, ID feature, it works in your system. If it doesn't work, there's no need to do that. First, we need to work. Second of all, it requires a frequent update because the information goes very dynamic. And the third scenario is in order to frequently update that, your system cannot support does not have this structure to support whole model updating. right? So because we are still dealing with about hundreds of millions or billions of coefficients. So with all these different scenarios, then yes, you can use this way to split your model as global and personalization part. Then you can frequently update this part, but leave this part less frequently updated. But if you can feed everything into your model, you have a very strong infrastructure to support everything, then okay, there's no need. Just put everything in one model. It's much easier. And this is just an example of such a structure called the GDMX framework. So you can have your global model trained by, for example, logistic regression, deep model, or some customized tree model. And for the personalization part, it can be a pretty lightweight model, because in the end, you only need to use this user's data to train such a model. It won't need like a lot of deep learning technology, not necessary. Sometimes for heavy user, maybe. Yeah, okay. So we talked about foundation model, global model, and the personalization model, and I just put everything together. Now, what's the difference and what's their role here? For foundation model, first of all, it is not a very task specific. Now, of course, there are still like a loss function we need to do, but it's not, compared to other models, it's not very task specific. It is to deal with large scale, complicated, unstructured data most of the time, and it is updated in a very low frequency, sometimes quarterly to yearly. Global model, it is task specific, say ranking model, and it mostly deal with structured data, and it can also get patterns from useful patterns from pre-trained model. And it is updated in a median frequency, monthly or bi-weekly. So last one is personalization model. Again, task specific, also deal with most of the structured data, and it can also get input from pre-trained model, but this will updating a very high frequency, say hourly or daily. And we put them together. This is pretty much one of the practice for foundation global personalization on the different scenario, treated by different purpose, updated at different pacing. Yeah. Okay. Actually, time flies. Come to the almost the last slide. Thank you for staying here with us. Fairness and stability. I just want to quickly share some thoughts here. Fundamentally, in a ranking system, when we talk about the fairness, it's mainly about you have two entities who have equally capability. And they are supposed to have equal access to the opportunity as well. From the user perspective, if two similar users looking for jobs, they're supposed to get a similar job recommendation opportunity. And from item side, if two hosts or products are similar, they're supposed to get a similar visibility. Okay. But this may not be the actual case in a real ranking system, because some minor randomness can cause big fairness impact, even if two entities are nearly the same. The job of ranking system is whatever provide a ranking list. So even there are two items very similar, in the end, they will still be ranked. There could be one item ranked on the top, but even with a slight difference with the next item ranked below. But it is what it is. You share this result to the user. Generally, there are position bias, and the user would like to, in general, click and purchase things they have seen first most of the time. So if you do that, you will see that the one ranked lower, even though maybe in the beginning is only one position lower, even though it is very, very close to the one ranked on top, still it is ranked lower. And gradually, the one ranked on top will get more engagements, get more purchase history, as the one ranked slightly lower will be pushed further down to the even next page or next level, then eventually disappear from the training data. And this is exactly the feedback loop causing the rich get richer and poor get poorer. And how to handle that? A few ways. One, we can always use exploit to make sure that the ranking model is not just sticking to this teeny tiny difference and always push something on top, another thing on the bottom. Secondly is you can use ranking ensemble to mitigate the bias. Yes, one model may be very stubborn to always think that one is better, but another model may think differently. But when you put them together, this random impact effect can somehow be mitigated. Okay, yeah, I think we have been talking about so many things here, and I just come back to the three categories of information: web search, online social networks, and e-commerce systems. What's for the future? There are so many things to do for the future. And today's topic is data-centric AI. why we are getting so many different types of data from their online engagement. I feel for such recommender systems, still it is challenging to capture the full journey of the user across online and offline. Sometimes we only know part of the offline, sometimes most of the time only know their part of online. How to collect more data from offline and collaborate that with the online data, then get a full picture of this user's journey is a continuous challenge that we can tackle. And the second is, especially for e-commerce system, those online engagements can be sparse. You can have hundreds of clicks, but you may only have a few purchases. And how to connect the dense engagement on click versus the sparse purchase engagement together, and to get a full picture of the guest intention, then further assist their journey understanding is another challenge. I think we can continue explore for the data-centric AI journey in the future. Yeah. Okay, I will stop here. Any questions? Before, oh, actually there's a QA here, but before we go to that, let me ask if there's any questions, happy to answer. Yes, please.
Yeah, well, thanks for your wonderful. I think there's like a verbal test and there are other informations. I think very insightful. And it's really like your slides about. Can you go back to that picture? It's the part is the foundation models, and the middle part is the role models. Yes, this one, and the right part is personalized models. Yeah, I think this is very great. For especially inspiring to understand how to really integrate foundation models to be the real impact for the specific tasks. But I have one small question is,
yes.
So now you can say we have foundation models and also the flow models and personalized models. But at the one time, right, we only require maybe just one of the personalized models is best fit for the user's current preference, right?
Yes.
So in practice, how do we really decide which models to use to provide the surveys, or
right.
This is based on the heuristics, or we have some knowable modules to do this?
Yeah, very good point, very good point. So that actually touched another benefit I didn't mention about ranking system management and fast iteration. Imagine if we have only have one model that pretty much cover all this kind of information, but they are in one model. So let's say you have 10 people want to improve this model, then their work may not be easily categorized, and they can even have conflict with each other. Like my change can affect your change. But here, we can actually have multiple people working on here, some people working on here, some people here, without affecting each other. It's more independent again. And then come back to your question is how we can evaluate which part works better. Because in the end, the model comes here, flowing to global to personalization. It still serves for the final goal, say ranking. And we can still evaluate offline wise, we can use NAUC or NDCG. And online wise, we can look at the business metrics. Say, look at the revenue, purchase, look at like booking rate. So that means if someone want to just work on the foundation part, but frozen this part, totally okay. And just evaluate whether a new foundation model version can improve the offline metrics further the online metrics. And the same for this part. They can freeze the global model and the foundation model, only improve the personalization model.
Okay.
Does this answer your question?
Partially, maybe my understanding is not that right. So here for personal models, it means different. For example, different learning target, like to improve the mix-through rate or to some other expectations. Does it expect this?
Oh, no. So you can imagine the final score is something about global plus personalization. In the end, the score is about the matching interest score.
Okay.
Yeah. Still like whether this user would be interested in purchase the item or click the item.
Okay.
Yeah.
Okay, that would be
yes. Thank you for your question. Yes, please.
How do you avoid the sound quality in this framework? Because you train one model, you feed another model.
Oh, could you say that again?
How do you avoid the sound quality because you're training one model.
Yeah.
You can independently to another model.
Yeah.
So you use feature data that you send to a model and then you use for another model. Is that correct?
Is your question about I have data to build this model, and then the same data will also be used for these components, so it may cause certain bias.
Temporally. Like timely, like temporal. Like you know, when you train on a model, you don't want to use like kind of future data.
Oh, yeah, I got it. Yeah. So, yeah, good point. Yeah. So usually for global model and a personalization model, they are under the same, they are kind of leverage the same tempo effect. So it's not like a personalization feature will be will take some benefit by a few weeks ahead or something, because they are all part of the training data. It's just the global model is trading those non-static feature. But the personalization model is using this global model is a static feature and the personalization model is using more dynamic features. But they are all treated at the same timeline and tested against something in the future. The challenge here is about the foundation model. So most of the time, we would like to find, I'm just giving an example. So if you use 1 year training data, and you use say last year until now as training data, and you use from now to the next end of next week as testing data, a better practice is probably use data from 2 years ago until last year for foundation model training. So therefore, you can kind of like split these components in terms of their different timeline, but no matter what, it won't get exposed to the testing data, which is happening in the future.
Yes, maybe I'm missing something there. But I can say is like you train a model, and then you feed this model into like global model or personalized model. But when you feed this model, your embedding or whatever you provide, actually use like feature data in the sense of like the new model, but you didn't know about this.
Yeah.
So that's what I'm trying to say. Like,
I got it. But do you think this would still cause a problem? Let's say in my example, if a foundation model is trained 2 years ago, using that 2 years ago.
I think foundation model is okay, but then you're missing information. Maybe you have to article that.
Yeah. So another thing is what if because the foundation model is trained on something non-task specific, it is not exposed to any engagement that is happening in the future. It's mainly about like whether the language speaking is more smooth in the semantic thing. Then for the global model, as long as I make sure that all the engagement feature I take is taking on the past, it is not taking on something in the future. Then, but this will, of course, in general, this is something like a big join to have, like you need to join by, if the user engagement join by user and a timestamp, not just join by user. Otherwise, it will involve what you have mentioned, this information leaking, the tempo effect. Yeah, feel free to ask me questions. I don't know if we still have time, but I'm happy to answer any question offline. Okay, so I think we can move to the final part, summary and the future directions. Again, thanks everyone for your attention and staying with us so far. So today we have talked about data-centric AI, and we have emphasized the importance of data-centric AI, which becomes the driving force for almost every AI successes. And we are talking about the training data, inference data, data maintenance, benchmark, and how to handle the fairness and the bias. And so the team just want to share a few thoughts for the future direction. Of course, welcome for your suggestions. First is about cross-task automation. While we are dealing with a single task most of the time on a certain domain, sometimes we are dealing with multiple tasks under the same domain. How can we deal with those tasks even across different domains? That is still some ongoing work. And right now we are mainly focusing about how to optimize data, optimize models separately. Like with one set fixed, another type to change to tune. How can we optimize them together and design them together? That's another thing. Yeah. And debiasing the data, we have discussed about the fairness and the bias, how to debias that, and how to tackle different data types with this modality: image, video, engagement sequence, text, excuse me, structured data, and in the end, with so many different components, tasks, and thank you also for your next question. What if we have this information flow? We cannot just use future to predict the past, right? So how can we have a robust benchmark with all the data sets accurately developed? Then no matter what kind of information leaking we have, it can be easily identified and fairly tested from this data set, including data benchmark and algorithm model benchmark. I think with that, I'm going to conclude this tutorial, and thanks for all the joint speakers. This is our, actually we have a survey here, and if you have time, if you can take that and just give out feedback, it'd be really, really valuable. Thank you so much. I'm going to ask all the speakers maybe come in front of the stage and just answer any questions here.